Let's hit record. Dogs are in the house. And for our final day, one more time, we are going to roll some tapes.
This is so sad.
Play the intro. Enjoy it while you can. Hello, space fans, and welcome to Professor Britton's Wacky Universe. All right, Astronomy 1020, welcome back to your final lecture. Today we're going to get into some groovy stuff. We're going to talk about white dwarfs. We're going to talk about neutron stars and black holes.
Yes.
We'll even talk about supernovae. It's kind of a lot.
Oh, I can finally ask my
Really
black hole
crazy.
question at the beginning of the class.
Say that, Mike?
I said I can finally ask my black hole question that I had on day one.
You can finally ask your black hole question today. Although I should get into it because black holes, of course, are going to come at the end, and we want to do that,
All right.
that treatment right. Okay, so what types of stars produce white dwarfs?
No idea.
Smaller to medium.
Everything that's not an O or a B.
That's correct. Both of those answers are correct. We have two main classes of stars now, okay? For today's lecture, we're going to lump low and intermediate mass stars in one category. And in another category, we're going to have high mass stars. As Hunter points out, O and spectral B type stars constitute.
That was Riker.
That was Riker.
Is 8 solar masses, okay?
It's the last class and he's still getting names.
Are we sad?
Oh, more sad that was Riker, not Hunter.
Oh. All right. So every time a star dies, it goes through a two-part separation. Let me share my screen with you here. Okay, so if I, hopefully all these PowerPoints are open. Let's go to my stellar death lecture. Started out with a beautiful looking nebula here. I believe this is the Carina Nebula, where Eta Carina is located. Do you guys remember Eta Carina? Eta Carina, I believe, is the overexposed star here. If you take a proper exposure, you can see what is, excuse me, essentially the death of a low mass star caught in the act of its final throes. These are what we call strong stellar winds. Basically, the last little splutters of fusion in the core of the star have gone so bonkers that they are basically pushing the outer envelope of the star apart. Remember that we did a problem set last week where we calculated the escape velocity from a red giant like Betelgeuse. And we discovered that a massive swollen star like Betelgeuse has a much lower escape velocity than a star like our sun. And that's because the gravity has been distended over a giant.
From Loto Z2.
Small amounts of radiation pressure are capable of just pushing the star apart. Now, it is not fair to say that when a star dies, it explodes, unless you're talking about a high mass star and a supernova. Low mass stars do not go supernova and they do not explode. And, you know, perhaps we should even take a moment to talk about this. An explosion has a technical definition. It's something like where the speed of sound is exceeded in your medium. And somewhere in this slideshow, I don't know why I'm jumping into this right now, but I just feel like it, I guess. Here's a little diagram showing you guys a sort of mock picture of how sound waves work, how you're able to hear my lecture today. Sound is a compressional wave. It's a longitudinal wave, which involves taking a gas, like the air in this room, and compressing it into regions of compression and rarefication, right? So the vibrations of my vocal cords are making pockets of air compressed and the compression of air results in a following expansion. And if you plot the pressure of the wave, you can see it's a nice little sine wave, just like any other wave in nature. Sound has a natural speed, depends upon, I believe, the temperature of the medium, maybe the density. And I believe the speed of sound is around 340 meters per second, typically for air at sea level at sort of an average room temperature. But it is possible sometimes when you do something violent to exceed the speed of sound by forcing something to travel faster than the natural compressional waves of sound want. Oh, sorry, I just heard an echo of myself. Anyways, let's take a look at this picture here. Here's a picture, I'm not sure if they did this in the infrared or what, of a bullet. Many bullets exceed the speed of sound. And when they do so, they create sort of like a snowplow of air molecules. What you're seeing here is a shock wave. This structure here is what's known as the bow shock. And it's basically a region, a super, super thin region of highly compressed and extremely high temperature gas. This bullet is forcing its way through the air molecules faster than the natural waves of sound want to go, resulting in, you know, what they call the sonic boom, or this shock wave here. This is what an explosion constitutes. To be an explosion, you have to push gas faster than the speed of sound. And there are many examples of this. It could be the report of a pistol. It could be the crack of Indiana Jones's whip. Hell, you can even make a sonic boom by taking a ruler and sort of placing it against your desk and pulling it back and snapping it. That sharp snap that you hear also is what's harsh on your ears is the compression of air that goes faster than the speed of sound. Now, the speed of sound in outer space is not going to be the same as the speed of sound. Oh, by the way, here's a picture of a supersonic jet. So some of you who are aviation enthusiasts may have gone to an air show where you've seen a high-speed jet travel faster than the speed of sound and make a sonic boom. You can see here the compression of the bow shock, where it's causing condensation of the moisture in the air into this sort of cone. Ooh, nice. Whoever did that, that was a nice
Riker.
Riker, cool.
Hey, Professor, if I can just jump in for a sec.
Yeah, actually, we should get so we have an explosion expert here. So let's hear what Zaz has to say about this.
Well, what I just wanted to say was just like a little sort of clarification, because people might be wondering, like, oh, you know, like if I put dry ice in a bottle and close it up and it bursts, that sort of seems like an explosion, even if nothing's breaking the sound barrier. It's technically a detonation, is where the shock wave goes faster than the speed of sound in the material. That's the difference. That's the difference. Yeah, that's the difference between a detonation and just a regular explosion.
Okay, so all right, so I needed this clarification. So an explosion can be just a burst.
Popping a balloon can be an explosion, right? Anything can explode, but that's what separates low explosives from high explosives. So a low explosive like black powder, you know, old school gunpowder, you know, if you put that in a sealed container and set it on fire, it will explode, but it won't detonate. And a detonation is what a high explosive does, and it's where the shock wave travels faster than the speed of sound in the explosive material.
Okay, this actually helps me, because one of the things that I'm constantly paranoid about is the difference between a low mass star death and a high mass star death has to do with exceeding the speed of sound. So it's a much more gentle puffing out of a star, but I suppose in a way that suggests we could call it an explosion. It's just not a detonation. Is that correct?
Yeah, yeah.
I just posted something in the chat.
Oh, what do you got there for us, Riker?
Explosion by definition.
Oh, a violent and destructive shattering or blowing apart of something. Nice, right. Okay, so if that's the case, if detonation is the only criteria, in that case, I suppose we could say all stars explode. The thing that makes astronomers usually hesitant about saying a low mass star explodes is it's kind of a much, it's certainly not a detonation. You do not exceed the sound wave, the speed of sound in the medium of the hydrogen gas. But it's also
every
a gentle,
star explodes, but not every star detonates.
I suppose so. But these low mass star deaths, they take a very long time. So much to the point where it's even like by the definition that you posted, Riker, it's questionable whether you could call it violent, because these stars just slowly begin losing material in the form of stellar winds. It's kind of like the solar wind, except there's a much greater ejection of mass material. As some of you know, recently we've had this kind of cool phenomenon happening this past year, where the brilliant super red giant star Betelgeuse had undergone a dimming in the sky. Did we talk about that in our classes, about how Betelgeuse was just
Little bit.
mysteriously getting dimmer?
Yeah.
It was absolutely amazing to see, as someone who's been paying attention to the sky for years, because if you, let me just grab that slideshow again. My opening slideshow has a really nice picture of the constellation Orion. And I'm going somewhere with this, so bear with me. You can see here in this earlier photograph of the constellation of Orion that Betelgeuse is clearly the brightest star in the constellation, followed closely by Rigel. Betelgeuse is one of the brightest stars in the constellation, followed secondly by Rigel. It appears to be a little dimmer in this picture, possibly because of the way the image was processed and what ratio of blue to red they used when combining their filters. But Betelgeuse is Alpha Orionis. That means it's the brightest star in the constellation. And this year, during the winter time, when I would go out and look at it, Betelgeuse clearly got so dim that it became dimmer than some of these belt stars, which are usually, Betelgeuse is like a magnitude 0.5, and the belt stars are usually a magnitude 2. But you guys might remember seeing it yourself. You could see that Betelgeuse had gotten dimmer than one of these belt stars. As you know, to drop by 1 or 2 magnitudes is more than a reduction of half in brightness. Now, the big question everyone was wondering is what's causing Betelgeuse to undergo this dramatic drop in brightness? One possibility was the star was undergoing a collapse that is the very final moment before a type 2 supernova where the star explodes, and people got very excited that they might be treated to this brilliant light show, which would clearly be visible during the day. It turned out, however, that to the best of our ability to research the thing, we were able to image this star using very, very large baseline interferometry, basically by combining a bunch of radio telescope data. And I want to see if we can find the picture here of Betelgeuse. The radio image of it, you could clearly see there was some dark blobs. Yeah, here we go. This is what we want. So this is a side-by-side image from January and December during the dimming. Now, Betelgeuse is the only star that we can just sort of barely resolve the disk for. And as you can see, at 55 milliarc seconds, we're not getting a ton of angular resolution there. This thing's pretty pixelated. But you can see here in January that the disk is reasonably well illuminated, where in this image, can you guys see that sort of darkening there on the disk? The leading interpretation of this is that Betelgeuse was undergoing so much stellar wind loss that the dust grains, the 2% metals, as the stellar winds left the star, were sort of cooling and solidifying into a dust cloud. You guys will remember that one of the effects of dust is extinction, the blocking of all wavelengths of light. And so this extinction from just cooled, solidified dust was so intense that it was causing the magnitude of the star to drop significantly on the sky. What's my point? My point is, if an explosion is just any kind of violent pulling apart of material, then we're still on the edge, I feel, of calling a low mass star an explosion, because it doesn't happen in a single, in a single instant. Where's my damn slideshow here? It takes a little bit of time. Let's see. Lecture 9. Oh, here we go. And Eta Carina would be an example of that. Of course, the time it takes for one of these stars to disassemble is still much longer than a typical human lifespan. So when we image something like this, it appears frozen in time, except it's very rare to actually get an image of a star like Eta Carida doing this. So actually, I think it's even simpler. Sometimes I just tell students stars blow up just because it's an easy thing to say. But there's a difference between what a low mass star does and what a high mass star does. Anyways, Zaz, thanks for that clarification, because this is why we like having you here, for some explosives expertise. Now, of course, at some point, the sun is going to do this. Here's a little illustration of perhaps the radius that the sun might reach another 5 billion years from now, as it leaves its main sequence phase and goes into its red giant phase. Typical red giants can swell up to 100 times their original radii. In the case of Betelgeuse, which is extremely swollen, Betelgeuse has a radius of 1,000 solar radii, making it comparable to the size of our solar system. And eventually the stars separate, whether they explode or whether they do not explode, into a kind of two-part model. In the case of low and intermediate mass stars, the outer envelope becomes what we call a planetary nebula. This is basically the cooled gas and dust that's returning to the interstellar medium. And then left behind is the little nugget that was formerly the nuclear core of the star. Class, do we remember what the final element is that is produced in a low or intermediate mass star through fusion?
Carbon?
That's right. So this thing is basically a little nugget of carbon. It is super hot. It's held together by degenerate forces. It's held together by electron degeneracy pressure. There's no fusion there to halt the collapse of this thing. And today we want to study these, what we call the remnants and the outer envelopes together. So quickly, just to put this into your notes, the things that we're trying to do today. For a lower intermediate mass star, your two-part model of death is the production of a planetary nebula, and the inner core becomes a white dwarf. This is all review of what we talked about at the end of last class. For a high mass star, you get something called a type 2 supernova. And as we mentioned last time, there is not one potential remnant, but two potential remnants to your high mass star. If they're a lower end high mass star, you might construct a neutron star at the core. And in the most extreme cases, where the mass of the core is, say, greater than 3 times the mass of the sun, that's when you can have the final collapse into a black hole. And of course, this is what we'd like to get to and talk about today. So let's get right to it, because there's a lot to say. Okay, first of all, I want us to talk about planetary nebula quickly. Planetary nebulae are some of the most beautiful things that you can image in your backyard telescope. When students come to my observatory, I take great pleasure in showing them the Ring Nebula, which is one of the brightest nebulae in the sky, and is an example of a dead low mass star. All the material that you see here, was once part of the outer envelope of the star. So this was all convection zone and radiation zone that now got sloughed off by strong stellar winds kind of blowing the star apart. Now, the word planetary nebula really doesn't, there's no such, it has nothing to do with planets whatsoever, okay? Who knows how this name came to be, but some of the first people to catalog many of these bright nebula were the brother and sister astronomy team, William and, oh gosh, Caroline Herschel. And William and Caroline Herschel took this great, I forget, it was like a 61-inch telescope in Ireland called the Leviathan, and they cataloged a lot of these bright nebulae for the first time. And of course, they had no idea what they were looking at, so the names they came up with things were fanciful and sometimes misleading. I'm not 100% sure we can attribute it to them, but it's as good a guess as any. Planetary nebulae, therefore, have nothing to do with planets. they're just beautiful and cool. And I think it's worthwhile to share some of my favorite ones with you. The Ring Nebula is awesome. Here's the Cat's Eye Nebula, the Eskimo Nebula. This is one that I've looked at through our telescope as well. The Ant Nebula. Look what's going on here. We actually see this in a a strong number of planetary nebulae that we see. We can see this kind of hourglass shape. Can you guys hypothesize what might be causing this, these sort of hourglass shape that you see in the Twin Jet Nebula? Why, when a star, I can understand a star puffing apart in a circular fashion, right? Like the Ring Nebula. But why do you think these stars might be sort of pushing apart in this?
Is it because of magnetic field?
That's probably the first good answer. I mean, if you think about it, you can actually almost see a dipole. You can see the shape of the dipole right there, right? We had a joke when we were graduate students that any time one of the professors asked us a question about space that we couldn't answer, we just said magnetic fields, and most of the time we'd be right. One, because people couldn't really test their theories that well with magnetic fields, and two, because, you know, usually if something was weird, that's how you'd explain it. So you can actually sort of see the dipole shape here. Rapid rotation could also play a role, as well as the angle at which you see it. Remember, if we were to look down the polar axis of this thing from a different direction, we might well see this as a circular expansion rather than as an hourglass shape.
Is it due to
Well,
like
it's weird, there's an eye
augmentation?
in it.
Hold on, wait. First, Sal, what'd you say, Sal?
Is it due to like the augmentation or like the buildup of matter that causes that shape?
Oh, okay. So no. So cool question. What's happening there is stars are.
Trees are cooler than space.
Wait, what's cooler than space?
What?
Ignore her. That's my sister. She
Oh.
studies trees.
I thought you were Zoom bombing us for a second there.
No.
I was like, oh, I'm gonna get Zoom bombed in my final lecture. This is great.
She studies trees.
Whatever she said was cooler than space. You tell your sister she's wrong. Okay, they ain't nothing.
You're wrong.
No, trees are way cooler than
They're
space.
not cooler than space.
Yes, they are.
All right, but hold on. Let's answer Sal's question because it's a totally.
Trees are pretty cool though, just to be clear.
Wait, what's cool?
Trees.
The-
That's
Is
what
that
she
what you're
said.
saying?
Trees.
Oh, trees. Yeah, trees are all right. You know, whatever. To answer Sal's question, stars are rapidly rotating. In the case of these low-mass red giants, they're sloughing off material in the form of strong stellar winds. Just like with our own sun, when it releases stellar winds, a high fraction of this material is in the form of charged particles. And these charged particles mostly take the form of extremely high-speed, relativistic protons and electrons. Relativistic meaning they're traveling faster than 20% the speed of light. Meanwhile, you've got these intense magnetic fields poking out of the star. Let's draw a magnetic field line. Now, in our lecture on the sun, I told you that plasma, or charged particles, stick to magnetic fields. And that's kind of true in bulk, but the real nitty-gritty, Sal, is that these particles actually oscillate and gyrate around magnetic fields. So I'm going to try to draw that here. Here comes my high-speed electron, and my high-speed electrons start oscillating and gyrating around the magnetic field lines. Now, if the magnetic field lines have a gradient in strength, which they almost always do, the electrons and protons feel a force that pushes them forward along the magnetic field lines. So this becomes kind of like a rail gun. You're basically using a magnetic field to sort of accelerate and push these plasma particles out into space. And as these particles get super accelerated, they smash into the surrounding gas, creating brilliant emission that we can see in the form of these jets. We saw a similar thing happen last week with protostars. Remember the protostars had these little tadpole legs kind of sticking off them? They were caused by a similar process there. So Sal, how this thing manifests itself, you're basically seeing high-speed particles getting shot along a magnetic field line and then colliding with surrounding gas to sort of heat it up. Just a couple more of my favorite ones. The Southern Owl Nebula. Look at this delightful picture of the Helix Nebula. And of course, we have to have our own humble contributions here. Me and the students last semester took this beautiful picture of the Dumbbell Nebula in the Jacobi 16-inch. Now, okay, ours isn't quite as high resolution as some of the professionals, but to make a picture like this, you usually have to stack something like 100 to 150 images in all the different filter bands, green, red, and blue. We did this composite picture with, you know, we had limited time because we were sleepy and we were doing it after class. But we did this out of, I think it was 10 red frames, 10 green frames. We had to get 20 blue frames because CCDs are less sensitive to blue light. And then we took 10 black and white luminances. So that was a total of 40 frames that we stacked together. And you can see our little humble picture from our Jacobi 16-inch. It looks somewhat comparable to, let's see, the Dumbbell Nebula. Anyways, I know a couple of you guys are photography buffs and some of you are taking photo classes. So at some point, it would be cool. I have some T-rings. It would be nice to take you guys down to the observatory once all this COVID-19 shit's done with and see if we can get you guys your own cool pictures of nebulae in space. It's not hard to do that. It's not hard to do this. It's just time consuming. So you can see here's a professional picture and here's our picture. Not too dissimilar. We got the right shape of the emission. Okay, enough said about that. Let's talk about white dwarfs. White dwarfs are basically a superheated, very hot nugget of degenerate carbon. You guys will remember that on our HR diagrams, do I have an HR diagram somewhere here? On HR diagrams, white dwarfs live down here in the lower left end of the spectrum. When we plot these things on an HR diagram, they're clearly not part of the main sequence, not part of the red giants or the supergiants. What does being down here on the main sequence tell us? Well, that's something I think you guys ought to know, right? What does being over here for Sirius B tell us about the temperature of our star?
It's a lot higher than the other stars.
Yeah, comparable to an O-type star. And that's because you're basically looking at the exposed nuclear core of a star. 30,000 kelvins, you know, is probably after it's gone through significant cooling once the outer envelope expands. Remember that the core of the star used to be closer to 15 million Kelvin. Of course, these stars are no longer undergoing active fusion. They kind of break our definition of star. In our class, our definition of a star was ball with fusion, and these things are kind of on the edge of that. Because they don't have active fusion, they cool over time. As they radiate away their energy, they slide backwards and downwards along this diagonal line, which is why we find white dwarfs distributed along this diagonal line. Over time, their cooling and their luminosities are decreasing.
They're kind of like skeletons, huh?
They're kind of like skeletons, yeah. Skeletons of stars. Or maybe just the skull. Now, we are supposed to know some things about carbon. Didn't we have a talk about our allotropes of carbon? What forms does carbon take in the natural world? I have a picture of it somewhere.
Diamonds are one of them.
Diamonds are one of them. What's the other one? Someone's got to remember.
It's not coal.
Graphite.
Yes, graphite. Remember, you can go to for a little light summer reading while you're falling asleep at night, you can read about the allotropes of carbon. And
summer reading?
Yeah, well, summertime's coming. You're going to need something to do, right?
Well, that's pretty heavy. That's pretty heavy.
Nah, it's like a gentle breeze, reading about the allotropes. Okay, hey, let's have a quick time suck on allotropes of carbon for a second. I want to tell you about this because all right, first of all, where's the damn picture that I want? I want the picture of the two main allotropes of carbon. For years, people believed that okay, I'm screwing this up. Somewhere there is a beautiful picture of the allotropes of carbon, and it's a sort of side-by-side comparison. Here we go. This is what I wanted. a nice side-by-side comparison of diamond and graphite. And you guys will remember that the difference between these two allotropes, they're both pure carbon, is in the arrangement of the lattice structure of the carbon atoms. Graphite forms itself into these sort of hexagonal rings and sheets, whereas diamond has a more tetrahedronal shape. Now, people thought for years that these were the only two possibilities for carbon to arrange themselves until a couple of clever chemists, I think at the University of Texas, Austin, predicted that it might be possible to take 60 carbon atoms and in just the right configuration to arrange them into a sort of geodesic dome they call a buckyball, after Buckminster Fuller, the famous New Wave architect, or a fullerene. And I know a little bit about this only because my electricity and magnetism professor at the University of Arizona, he was Donald Huffman was the first person to actually synthesize these things while experimenting with some vacuum tubes. He actually just stumbled upon them completely by accident. He found this carbon soot that had no known spectral signature to any other form of carbon. And he eventually figured out, oh my gosh, I've found myself some buckyballs here. And buckyballs are pretty darn weird. Apparently you can place another atom inside of a buckyball and it will kind of bounce around. And it gives these things some kind of strange properties. For instance, if you youngsters are fans of the Disney movie Flubber, I guess that slime in Flubber, I did not see Flubber for the record, but I've heard that the slime in Flubber was made from buckyballs. And this began a cottage industry in new and exciting forms of construction of graphite, right? People realized that it might not only be possible to make 60 carbon buckyballs, but actually create spheres of increasingly greater number of carbon atoms, right down to these infamous carbon nanotubes, actually construct them into rings and tubes. Now Zaz might, as a former chemist, might have more insight on this than I do, but I feel like the future of technology is definitely going to be heading in this direction, because graphite, I believe, is capable of conducting electricity or a current under certain conditions. And that means that in the future, you know, they're already making these little LED screens out of contact lenses, but in the future, you're probably not going to use your phone to log into Facebook. You're just going to twitch your eye or something. Cybernetics is coming, okay? And it's I feel like it's inevitable. Pretty soon, people are going to start integrating these carbon sheets right into their skin. It's completely amenable to the human body, unlike metals. Anyways, suppose you had to take a guess about the nature of a white dwarf. We have some highly compressed degenerate matter, and it's carbon. Do you think it would more likely be graphite or diamond, or do you think we got buckyballs down here? What's the most likely form for this carbon to take? Could white dwarfs be like a diamond in the sky? Let's see here. Here's a model of a white dwarf. Pardon?
Wouldn't be
No, so I thought you were making
heat and pressure.
And it hurt me.
Say that, Tim. Pressure is at the heart of what I'm trying to talk about here.
There's a lot of heat and pressure, so wouldn't it be diamond?
You'd think, right? But even diamond, okay. Normal carbon, whether it's in the form of graphite and diamond, has a density kind of comparable to rock, right? So let's go to our periodic table of the elements, Sergeant Welsh. And I'm trying to do something here, so just bear with me as I take you through my gyrations of thought. I want to get my high resolution Sergeant Welsh table, and I just want to look at what the standard density of carbon is, okay? So here we go. Let's open up this tab, and let's hunt around for carbon density in grams per cubic centimeters in blue here. 2.26 is the typical density of both carbon, whether it's in graphite or in diamond form, okay? Now, white dwarfs are highly compressed material. You can see here that a typical white dwarf will oftentimes contain something close to the mass of our entire sun, but will, pack it into a radius of about 6,000 kilometers in dimension, or in length. That's comparable to the radius of Earth. So you're smushing the mass of the sun into a sphere the size of Earth. What if we just took a moment to calculate the density of such a star? It's our last lecture, so I got to make you guys do some math. Otherwise, I'll feel like I've missed an opportunity to torture you. So, as you guys know, let's try a little sample problem where we find the density of a white dwarf. Now, density, as you know, is mass over volume. And the volume of a sphere is 4/3 pi r cubed. Meaning, if I give you the shortcut version, the density of a sphere of radius r is 3 times its mass over 4 pi r cubed. Let's take typical values for a white dwarf, like Sirius B. If the mass is the same as our sun's mass, you've got something like 2 times 10 to the 33 grams, and the radius of Earth is 6,400 kilometers multiplied by 10 to the 5 to convert it to centimeters. Why don't we plug these numbers into our formula, and you guys do the punch-in and tell me what you get. 3 times 2 times 10 to the 33 grams over 4 over pi over 6,400 exp 5 centimeters cubed. I want a number.
Well, let's see, it's, I gotta count the places. 1.8 times 10 to the 7.
Can someone else verify that? I just want to make sure it's not 6.
It might, it's a million. It might be 6.
Wait, is it 2 million or is it 20 million? Count the zeros.
Oh, hang
Did
on.
anyone else do this, or we just
What's that radius? I can't quite read that.
Oh, I wrote it in a really douchey way. I wrote it as 6,400 times 10 to the 5 centimeters.
Oh,
I was
okay.
kind of lazy.
It's 1 million. It's 2 million.
It's
sorry,
2 million. Okay,
Yeah.
so that's what I was expecting.
So I was having trouble counting because my calculator doesn't. This isn't enough light for it apparently. So I have to do this.
2 million grams per cubic centimeter. 2 million grams per cubic centimeter. Does anyone understand the point that I'm trying to make? What's my point? How does that compare? Let's go back to our Sergeant Welsh periodic table for a second. According to our legend, these densities were taken at 300 Kelvin, probably at standard room pressure of 100 kilopascals. Carbon and diamond have densities of 2.3 grams per cubic centimeter. What's my point?
It's dense.
Yeah. Okay, that's my first point. My point is, this ain't your pappy's carbon, okay? This ain't no diamond. This ain't no graphite. This ain't no buckyball. Imagine taking a little hammer and smashing these atoms into little bits and then just smushing them all uncomfortably close to each other. This material is not under any normal sort of crystal lattice. These carbon atoms have been awkwardly herded together and smushed into a little tiny volume of space that is much closer for comfort than they would typically like. This is how a star supports itself from gravitational collapse into a black hole, how a white dwarf does anyways. This material is being held together by quantum mechanical forces. It is literally the quantum mechanical repulsion of the electrons that's preventing this star from collapse. let's take a couple of quick notes on this. Okay.
Wait, like if you tried to harvest anything from that, like do we have any tools on Earth that would be able to cut through that?
No. In fact, I think if you tried taking your tools there, they would gravitationally get stuck to the surface and compressed into a puddle of atoms. You know what? It would be kind of cool to calculate the G-force. What is it? Gm over r squared, right? Like on Earth, we're at 1g, 10 meters per second squared. 7 exp minus 11 times 2 exp 30 divided by 6.4 million squared. 1, 2, 3, 3.4 million. 3.4 million meters per second squared. Divided. So,
Basically, if you tried taking your tools there, not only would your tools become a puddle, but as would you.
yeah, it's 300,000 G's at the surface of one of these things. Come on, Mr. Autofocus.
Well, I meant like even like in a sandbox, like that aside, like I was just talking about the density because I was thinking about how hard it is to cut diamond. So,
Right. So if you took a sample of, I understand what you're saying, but if you took a sample of that material away from the white dwarf, which you would need to do, it would probably instantly expand to something like, well, I think it would expand. I guess I'm not 100% sure. My point is those atoms do not want to be sitting that close to each other. It's uncomfortable. It's awkward. There aren't many places in the universe where you can do such a thing. Let me try turning the intensity of my background lights down. Maybe this will help with my autofocus a little. Okay, so things that we want to know about white dwarfs before we move away from them. There's a couple of extra things I got to tell you about. So a typical white dwarf contains something like 1 solar mass of material. That's pretty standard. And the radii are pretty close to an Earth radius. So you're packing the mass of the sun into the radius of Earth.
the autofocus is all fucked up. Oh.
I know. I don't know what's going on here. So they're usually made of carbon. Although there are oxygen white dwarfs or carbon oxygen white dwarfs. Typically, the material is held in hydrostatic equilibrium by something called electron degeneracy pressure. You guys will remember from our last lecture that degeneracy pressure means the electrons are sort of pressed up against each other in terms of their quantum numbers, and they're unable to get any closer due to the Pauli exclusion principle. Basically, the electrons are traveling at relativistic speeds, and they're pressing up against each other, and they're unable to get any. They prevent the star from getting any closer together. Oftentimes, white dwarfs are not found in isolation, but oftentimes they are found in binary pairs. And that's because you guys will remember that about 50% of the stars that you see in the sky are actually part of a binary system. And that's kind of cool because we actually have an image. We actually have an image of a white dwarf. Normally their luminosities are so small that they're almost impossible to see. So here's a little old school astronomy lesson for you here. You guys, once again, can recognize the constellation of Orion, seen over here. And as we've said many times, the brightest star in the sky is the star Sirius, which is the dog star. It kind of follows Orion at his back foot there as he travels east to west across the sky. Now, it's possible because it turns out that Sirius is actually a binary star in which the companion Sirius B is a famous white dwarf. And it's actually possible to image this thing. This is a spectacular image here where we can see the intense luminosity of Sirius A. And they've managed to expose this photograph in just such a way where you've got Sirius B there. Notice, remember, you're not seeing the sizes of the stars because they're essentially point sources. but you're seeing the differences in their luminosities here, since they're at the same distance. Look at how much more luminous Sirius A is than Sirius B. And that's entirely due to its radius. You'll remember that the luminosity of a star is strongly dependent on its radius. And these things are incredibly small. So the only reason we're even able to see this white dwarf is because it's 8 light years away. Okay, what happens with these binaries is from time to time, they find themselves in a situation where the stars might form at the same time, but they form with different masses. And you guys will remember that the mass of a star strongly influences how long it takes to go through its nuclear fusion. So let's imagine we had a scenario here in which 2 stars formed, and one became a red giant just a little sooner than the other. Maybe one star had a 2 solar mass, and the other one was maybe 1 solar mass. The 2 solar mass star is going to live for a shorter period of time. What can happen is that one star can puff off its outer envelope, leaving behind a white dwarf that's in a binary companion with a star that suddenly becomes a swollen red giant similar to Betelgeuse. Now, both of these stars have gravity, and at some point, there's some kind of an equilibrium tipping point that exists between the 2 stars, where if you placed a little test particle, like a little floating astronaut or a little block of cheese or something, that object would feel an equal gravitational force from the white dwarf that it does from the red giant star to the left here. And also the fact that these 2 stars are rotating means that there's an equilibrium point due to, centrifugal forces that exist in a whole figure 8 shape surrounding the 2 stars. It can sometimes happen that at the end of a star's life, its outer envelope swells past the so-called Roche lobe, or the gravitational tipping point, and then plasma can begin to spill off of the envelope of one star and in spiral down onto the surface of the white dwarf. Stars might not be collisional in space, but gas is collisional. And the fact that the gas rubs against itself and has friction means, just like those ball bearings we saw at the Museum of Science in the gravity well, these things can slowly in-spiral and lose energy until they find themselves plopping down on top of the white dwarf. And when that happens, some pretty cool things start to happen. Because the white dwarf is essentially an exposed nuclear core of a star, the moment this plasma strikes the surface of the star, it can undergo violent bursts of nuclear reactions that send intense globs of X-rays out into space. This is what is called a nova. It's an intense brightening of a white dwarf. Also, every time we add matter to a white dwarf, we're increasing its gravity, but we're not necessarily increasing its internal pressure. One of the rules that one learns about electron degeneracy pressure is that the ideal gas law no longer holds. And that means pressure is no longer connected to temperature. Pressure is instead related to basically quantum mechanics, or the Pauli exclusion principle. And the fact that pressure and temperature become divorced from each other is interesting, because it means if you add material to a white dwarf in one of those high mass transfer binaries, you're going to be increasing the mass of the star, and that tends to squeeze the star down. Here's a little crappy animated GIF showing you what's happening. Every time you drop a little bit of material onto the star, you're adding mass, you're increasing its gravity, but the electrons are still fighting each other to keep this star from collapsing on itself. Now, there was a legendary astrophysicist who began toying around with the calculations for a white dwarf using general relativity just a few years after Einstein had developed his theory. You'll remember that Einstein's theory of general relativity was developed in 1915. And as a young man, Subramanian Chandrasekhar, a famous Indian astrophysicist, took a boat ride from Bangkok to England to meet the great master Stanley Arthur Eddington. And maybe to impress him, he began performing a calculation on what would happen to a white dwarf if you continued to compress it until the electrons inside started to move so fast that they approached the speed of light. His brilliant, ingenious insight was to realize that as you compress a white dwarf, the electrons inside of it will travel faster and faster and become relativistic to the point where they will push up against the speed of light. Knowing as we do that nothing can travel faster than the speed of light, he deduced that this would be the breaking point of a white dwarf. And his final calculation is actually kind of worth taking a peek at. Physicists make a big deal out of what's called the Chandrasekhar mass limit of a white dwarf. It's a little bit over our pay grade in this class, but that's okay. We can still take a peek at it anyways. After performing this brutal calculation using general relativity, he finally came up with this legendary formula here. And I want you guys to take a look at it. He computes that if the electrons inside of a white dwarf travel at the speed of light, the highest mass a white dwarf should be allowed to have is based on these factors here. Now, don't worry about this little doodad. That's just a number, 2.01. And you guys know 3 and pi and 2. But take a look at the fundamental constants that appear in this equation. First of all, there are no variables. It's just fundamental constants of nature. And we have, in no short order, big G, which is a symbol of the gravitational influence of the white dwarf. We have Planck's constant, which always appears in calculations involving quantum mechanics. We have the speed of light, which tells us that relativity is involved. And we also have the mass of a hydrogen atom. All of these numbers are fixed properties of the universe that Mother Nature herself has invented. And that kind of means that Mother Nature has fine-tuned the equations of physics and given us the maximum limit that a white dwarf can have. So I don't know, physicists kind of geek out over this. They think it's cool that when they finally solve this calculation, it turns out that the limit to a star, which is this macroscopic thing, can be dependent only upon fundamental constants of nature. And the limit that you reach when you put in all of these values is 1.44 solar masses. That's the so-called Chandrasekhar mass limit. What should happen if you exceed your Chandrasekhar mass limit? I'd like to show you. Where is it? It's supernova 9. Do I have it? I know I have a picture of it somewhere. This guy here. If a white dwarf, shoot, I already forgot what stupid slide that was. If you should compress a star past its 1.44 mass limit, solar mass limit, excuse me, you will get one of the most violent supernovas that exist in nature. Even more violent than a high mass star supernova because it's powered in part by relativistic effects. Here's a legendary image of a galaxy, NGC 4526. This thing is billions of light, well, hundreds of millions of light years away anyways. And this is one of the few examples where we just got a lovely picture of a white dwarf supernova going off in the outer spiral arm of this brilliant spiral galaxy. Now, keep in mind that at galactic scale distances, you normally cannot see a single star because even the brightness of the point source is too faint for us to detect. For instance, if you look here, this is the bulge of the galaxy. And that's not a star, my friends. That's a sphere of stars that probably contains 1 billion stars and has a luminosity of 1 billion solar luminosities. So that little nugget that you're seeing there is probably close to 10 billion or 1 billion solar luminosities. Now, when a single white dwarf that's about 1.5 solar masses explodes, its luminosity, as you can see here, can rival the luminosity of 10 billion stars smushed together in a ball. And you can see these white dwarf supernovae at what we call cosmological distances, at distances at which the galaxies are increasingly farther away from the Milky Way. And because they always explode with the same mass, they always explode with the same luminosity. And these white dwarfs are tools, these white dwarf supernovae are tools that astronomers use to help them calibrate the distance to galaxies. In fact, one of our problem sets today, we're actually going to compute the distance to a galaxy based on the fact that these type 1a supernovae usually max out at 10 billion solar luminosities. Sorry, I'm not saying all this well because I'm thinking about the stuff I want to do next. So let's just take this final note about white dwarfs, and then we'll move on to neutron stars. The key idea is that there is something called the Chandra, oh my gosh, Sekar mass limit for a white dwarf, and this is the maximum mass a white dwarf can have. It's 1.4 solar mass units. Anything greater than that will turn into what's called a type 1a supernova, or what's commonly known as a white dwarf supernova. Typical luminosity, the standard luminosity for a white dwarf supernova is 10 billion solar luminosity units. And this is what's called a standard candle in astronomy. A few years back, was it Martin? I forget the name of the astronomer now, but he, one of the Nobel Prizes in physics went to an astronomer who was studying the recessional velocities of white dwarf supernovae in distant galaxies. And he conclusively proved that there was some kind of mysterious dark energy flinging galaxies apart based on the fact that these white dwarf supernovae were traveling at speeds much faster than they should be at these galactic distances. So a lot of interesting modern astronomy research depends upon these white dwarf supernovae. I don't have time to get into all of it, but I'm tantalizing you to go and find out more yourself. Okay, let's take a little think about some high mass star death and think about neutron stars and black holes while we still have a chance. So what's the deal with a neutron star? It's a lot crazier than a white dwarf. And one of the reasons has to do with the way that, that neutron stars are formed. I need to go back to a slightly earlier slideshow, and I want you guys to remember what the interior of a high mass star looks like shortly before its death. You'll remember that there's a sort of onion skin layer to fusion in a high mass star, where stars are high mass stars are increasingly creating heavier and heavier elements through more exotic processes in fusion. First, they form carbon into oxygen and neon and other elements through helium capture, and then the large nuclei start to slam together on their journey towards iron. Each one of these reactions takes an increasingly shorter amount of time, to the point where I believe that silicon fusion to iron fusion, we've calculated, takes about 15 minutes. It takes 15 minutes for a high mass star to go through its final wave of fusion into iron. Once you develop a nugget of iron in the center of your high mass star, that iron nugget is warm, it's degenerate, but it's not capable of going into any higher levels of fusion unless it sucks gamma rays out of the core of the star. And this leads to a collapse that sometimes people describe as neutron star bounce. Basically, the entire outer envelope of the star suddenly feels no supporting pressure from fusion, and it begins to infall on itself, smashing into a degenerate nugget of iron. And the process is so violent, in fact, that it basically breaks degeneracy pressure instantly. What does it mean to break degeneracy pressure? Well, it essentially means that you're taking the electrons, which are kind of zipping around inside the iron nucleus, you're pressing them into the nuclei of the atoms. And you guys will remember that you can take an electron and a proton and you can smush them together to make a neutron. And you create a ball of neutrons, you create an intense flux of neutrinos, and the neutrinos, although they're normally ghost-like, actually help propel the star into the type 2 supernova. Of course, what you're going to get left behind is basically a giant ball of neutrons. And that's what a neutron star is. Let's take a little imagination trip here into the heart of a neutron star. So typically you're dealing with a mass that's already above your Chandrasekhar mass limit. Otherwise you'd be a white dwarf. So you start neutron stars somewhere around 1.5 solar masses, but they typically have a radius of about 10 kilometers. And they're held together by a different type of degeneracy pressure called neutron degeneracy pressure. Apparently neutrons also obeyed the Pauli exclusion principle, and they cannot occupy the same quantum state. So typical neutron stars, the mass ranges are somewhere between 3 solar masses and 1.5 solar masses. It turns out that around 3 solar masses, you start getting close to black hole territory. The radii are highly compressed. 10 kilometers for a radius, that's about the size of Boston, right? So you're squeezing almost 2 solar masses into a volume of space that's similar to the city of Boston. They're held together by neutron degeneracy pressure. And of course, I don't think I need to mention this, but just in case, remember class, if you have a giant ball of neutrons, that substance no longer appears on the periodic table of elements. You'll remember that we define an atom by its number of protons. The number of protons in a neutron star is, well, in principle, 0. That means you're basically dealing with a sort of giant atomic nucleus, right? This thing resembles a giant atomic nucleus more than it does a ball of carbon or some other material. I'm not going to calculate the density of a neutron star because we're going to do that in our problem set today, but obviously it's way crazier than that of a white dwarf. 2 million, our white dwarf came out at 2 million grams per cubic centimeter. The densest material in the periodic table is like osmium, and that's maybe, I don't know, 23 or 24 grams per cubic centimeter. Nothing is certainly above 30 grams per cubic centimeter on the periodic table. Neutron stars have intense gravity. In fact, these things are really, technically a white dwarf is not a relativistic structure in terms of gravity because the escape velocity of a white dwarf is usually around 2% the speed of light. Do you guys remember the cutoff velocity for relativistic gravity? Maybe I'm talking too much here. It's 20% the speed of light. Let's do a little sample problem. Let's find the escape velocity of a neutron star. Remember that the escape velocity is 2 times big G times the mass divided by the radius. And we're going to plug in 10 kilometers and something like 2 solar masses to see what we get. Times 7 times 10 to the minus 11 meters cubed per kilogram per second squared. 2 solar masses is 4 times 10 to the 30 kilograms. And we'll divide it by, well, 10 kilometers is 10,000 meters, right? What do you get if you punch that into your calci?
5.6 times 10 to the 16th.
Did you forget the square root?
Yes, I did.
All right, so do that.
Okay.
So what do you get when you square root, Riker?
2.4 times 10 to the 9th.
Count better. You can't be 2.4 times 10 to the 9 because then you'd be faster than the speed of light.
Oh, 2.4 times 10 to the 8th.
Okay. And if the speed of light is 3 times 10 to the 8 meters per second, what percentage of the speed of light are you traveling at, or would you need to travel at to leave the surface of a neutron star?
Do that math in my head.
That's damned, that's
80%.
That's 80% the speed of light.
Basically, you stuck there.
Yeah, well, photons can, even photons themselves can barely get off the surface of the star. Photons leaving this is one of the reasons why you can't see neutron stars. Their radii are so small that they don't give off very much light. And even that light that does come off the surface is so gravitationally redshifted that it's practically visible light would get shifted into the infrared just trying to get off the surface of these things. So another point that I'm trying to make by doing that calculation, my friends, is that this thing is really teetering on the edge of a black hole. A black hole, of course, is something in which you are at the speed of light. So these things are barely even keeping themselves from collapse due to gravitational pressure. Now, because I want to get onto black holes before the collapse ends, I'm just going to tell you one cute little story about the history of neutron stars. These things are, of course, they were theoretically proposed or imagined before they were ever detected in real life. It's not easy to detect a neutron star. And let me take you back in time to the 60s when people started building the first radio telescopes to sort of, you know, post-World War II, when there was this huge development in radio technology, there were some weirdos like Grote Reber and some other famous radio operators that began constructing the first radio telescopes to search for radio signals from space. And this famous astronomer, Jocelyn Bell, was a graduate student in the 60s, and her advisor, Anthony Hewish, had basically constructed one of the first radio telescopes, which they didn't look like the fancy antenna dishes that you see today. They kind of looked like the old antenna that you see in your grandpappy's trailer park there. They kind of look like a bunch of mesh wires that were spread out here on the English moor. And as a graduate student, it was her job to go and capture the radio signals from space and analyze them. And they found that every time the Crab Nebula came up overhead in the sky, they found a little pulse of radio signals with this perfect periodicity of 33 milliseconds. So they were basically looking up at the sky at radio waves, and they were seeing a little blip of radio burst, and then it would go quiescent, radio burst, quiet, radio burst, quiet. And the pulse came with such perfect regularity, and it came with such a rapid frequency of 33 milliseconds that they for a while struggled to imagine what astrophysical source could have such uniform periodicity and could have such a short period of short period of oscillation. For a time, they actually decided, they codenamed this research LGM. And LGM was an acronym that stood for Little Green Men. They literally thought a hyper-intelligent alien civilization was trying to contact them with radio Morse code because they couldn't imagine that any natural astrophysical process could create such a perfectly uniform frequency. It's said that the period of these so-called pulsars rival that of those atomic cesium clocks we mentioned last week. Okay, Jocelyn Bell was clever enough to have heard some hypothetical ideas that perhaps neutron stars during collapse could drag magnetic field lines along with them and create hyper-powerful magnetic fields. And she eventually kind of constructed this sort of hypothesis here that what she was looking at was a rapidly rotating neutron star in which the magnetic axis of the star was not in perfect alignment with the rotational axis. That's not far-fetched. You guys know that there is a deviation between geographical north on Earth and magnetic north of whatever it is. It's 12 degrees or something. So even on our own planet, we have a deviation between our rotation axis and our magnetic axis. She realized that just like I told you earlier, how magnetic field lines can sort of accelerate charges, that if these magnetic fields were to oscillate in such a way where they pointed towards Earth, we would get a little burst of radio light. And the fact that the neutron stars were so small, only about 10 kilometers in radius, would mean that they had to have extremely rapid rotation after collapse. And the time scales all kind of worked out. Anyways, her advisor thought this was such a cool idea that he took all of her research and won the Nobel Prize for it a couple of years later. So
about right.
kind of yeah, so Anthony Hewish has the, I can't remember the exact years, it's in the 60s, I believe. He has a Nobel Prize for the discovery of pulsars. But apparently, the legend goes that she did all the work. Was the Nobel Prize. 1974, a Nobel Prize in physics. Big controversy in astronomy. You guys can read about that. Okay, we got a few moments left, not many. Let's talk about black holes. A black hole, of course, as they say, is the ultimate victory of gravity. In those situations in which the core of a high mass star can be compressed above the 3 solar mass limit, you suddenly achieve the speed of light as your escape velocity. And hypothetically, at that point, there should be nothing to prevent the gravitational collapse of your material into what's known as a singularity. Now, in our class, I have a very particular picture that I want you guys to imagine for a black hole, and it's something like this. In theory, for a non-rotating black hole, what is known as a Schwarzschild black hole, the entire mass of your star, 3 solar masses in all, should collapse into a point of 0 dimensions. Now that sounds a bit absurd. How can something actually have 0 dimensions? But because we don't know of anything after neutron degeneracy pressure that can halt the gravitational collapse of a star, in principle, this thing can just continue to crush itself down to 0. Now, some people believe that you shouldn't actually be able to get to 0, that there, in the same way that there's a neutron degeneracy pressure, there's some kind of a quark degeneracy pressure that exists below this limit. Perhaps you can have actually a quark star inside here. But it kind of doesn't matter, because once the thing goes past the escape velocity of light, photons can no longer escape your singularity. And there's a sort of window of last return that you cannot see through. So in other words, while the black hole itself is a microscopic dot of matter, there exists this boundary called the event horizon, where you've exceeded the escape velocity of light, and therefore photons which cross this barrier can only travel inwards and not outwards. Without photons, you have no way of observing this object, and therefore it's kind of something of a black box mystery. If you use this artist illustration here, if you could fly close but not too close to a black hole, you'd probably see this dark sphere, a place where, first of all, light would start acting pretty funny close to the event horizon. Photons can actually be curved and warped by the strong gravitational fields of a black hole. So you might actually see photons doing some funny things in the nearby vicinity. But you can actually compute this Schwarzschild radius with a pretty straightforward analysis, starting with your escape velocity formula. So let's go ahead and do that together, because that's an instructive little last-minute exercise here. Also, we're going to need this formula for our homeworks today. At its most basic, the definition of a black hole is just any object whose velocity exceeds the speed of light. Sorry, I've got some camera issues here. What do I do? Sometimes
Get a new camera.
Well, yeah, that's what I did.
At this point, there's no reason to.
Well, I've got to teach in the summer too, but yeah.
Oh, never mind, maybe.
Okay. Let's take our escape velocity and let's set it equal to the speed of light. Any of you guys have the algebra chops to pull this off? Now, in the original analysis done by a famous astronomer named Carl Schwarzschild in 1919, I believe. This is 4 years after Einstein's theory of general relativity was published. Carl Schwarzschild did a more advanced analysis which sadly came out to the same answer we're going to get with this stupid algebraic one. Kind of a sad story with him. He was 21 years old when he published this paper on the so-called Schwarzschild radius, what the radius of a black hole should be. And it was the only paper. It was a brilliant analysis. He did the whole thing in with general relativity and tensor calculus. But famously, he either volunteered or he got drafted into the German army and went into the trenches in World War I and got shot. So this was the only paper that he published at 21 years old, and then got lost to World War I. If I set this equal to the speed of light, I can choose to solve for the mass of the black hole in terms of the radius. But Carl's idea was to solve for the radius and say, if I have a black hole of this many solar masses, if it's 3 solar masses, what will be the boundary of no return, the radius of the event horizon that light cannot escape from? So which one of you guys have the algebra skills to solve for the radius here? I could always pick a volunteer, like Nathan. Nathan, I feel like you have the algebra skills to do this. Get that chicken back here on the camera.
I knew you'd call me. I don't know why. I had a feeling. I don't know if I have.
Well, you got to.
algebra
I mean, have you got? What do you do with that square root?
You
How do you kill a square root?
square everything inside of it.
Oh, you square everything outside of it on both sides of the equation, right?
Yeah. Yeah.
Okay. So I'll get rid of that and I'll put c squared over here. Now what am I going to do?
Maybe put like fill in like what G, M, and C are.
No, we don't want to put numbers in. That's for losers. We like to see it algebraically.
Yeah, I was thinking that.
Can I hop in?
Only losers put the numbers in. We just.
Hey, I like numbers.
Yeah, they're all right.
Loser.
I've been called.
Come on, you've got one step. You can do this in one step. Someone knows what to do.
Switch the R and the C squared.
Yeah.
You got it.
You know, on a good day, I might have been able to do that, but it's the last day, and I just didn't come.
The last day is
That
a
makes
good
it a
day.
good day.
I just didn't come with enough.
I mean, a sad day.
And this equation, my friends, is known as the Schwarzschild radius. It's not exactly the radius of the black hole. It's the radius of the event horizon. So let's make a little picture here. Here's your singularity. There's your black hole. And then there's this imaginary invisible sphere surrounding it. And that is your Schwarzschild radius. In a funny way, guys, any object that has mass has a Schwarzschild radius. And there's a kind of funny interpretation of this. Any material could be, in theory, compressed into a black hole if you take that object and you continue to shrink it past the point where light exceeds its escape velocity. For instance, our sun, this is an interesting exercise. 1 solar mass, or 2 times 10 to the 30 kilograms, in theory, could be compressed into a black hole if you could squeeze it down to a radius at which gravity would sort of overpower the speed of light. Why don't we plug in those values as a quick little sample? 2 times 7 times 10 to the minus 11 will work in MKS units, times 2 times 10 to the 30 kilograms, divided by 3 times 10 to the 8 meters per second squared. I'm zinging you with just a few more math problems before I let you out the door here. Although I guess I get to torture you a little more in office.
Yeah, I was about to say, what do you mean? We still have a lot to do.
Actually, today's homework is wicked easy and fun.
Oh, okay.
Today's homework is fast. 45 minutes tops, I think.
Oh,
And by the way, all of this is training for your homework because this stuff's going to be in there. So I want to tell you some fun things about black holes too, but you have to know some basics before I can do that.
I have a basic question about black holes.
All right, sure.
Are they spheres? Or is it because, I mean, you said it has no dimensions, but I don't know. It's kind of a weird concept.
The Schwarzschild radius is certainly a sphere. Nature tends to favor spheres because it's the, minimum surface area to maximum volume. But I'd say I can't think of a clever reason to say yes, but I certainly have no reason to say no. So I think yes, the general consensus is there's spheres. Here's the one tricky thing, Mike.
I have
3,000.
3,100.
Sorry?
3,000.
I have 3,100.
3,000. All right, let's call it 3,000 what?
That would be meters.
Yeah. How many kilometers is that?
3.
Okay, that means there's a shortcut for the Schwarzschild radius. It's approximately 3 kilometers times the mass of your star if you measure it in solar mass units. So 3 kilometers is pretty small, right? That's like downtown Providence. If you could smush the sun into a volume comparable to, actually 3 kilometers might even be too big for downtown Providence. 3 kilometers, it's not a great distance in terms of astrophysics. So that's a pretty highly compressed star. I want to answer. I only have time to say one more cool thing about black holes, but I want to do that while answering Nathan's question about is it a sphere. So I actually do know the answer to this question. Because general relativity is required to analyze a black hole, you need to perform very involved calculations using tensor calculus, which is like a multi-dimensional mathematics. I've got a nice book here where you perform the calculations in general relativity. You guys can actually find this on the internet. It's a legendary general relativity book known as the Green Shoots book by astro students, and it's your first course in general relativity where you bust out the hardcore tensor calculus.
Actually, I think I found it as a PDF, and I think I downloaded the thing.
Yeah, check this thing out. Some of the descriptions are nice, but the mathematics, let's just say it's aspirational. If you guys can get towards this, then you're going to come back and visit me one day, and you're going to correct all of the errors in my lecture presentation. You're going to be a guest speaker like Zaz who can enlighten me on the ways of general relativity. But here's what I do know from having muscled my way through that book. There are only 2 analytical solutions to a black hole, 2 solutions where you can actually perform them with a piece of paper and a pencil and solve for what is the nature of the black hole. And these 2 solutions are simplifying solutions. The first one is what's known as the Schwarzschild black hole. And that's where you assume that the black hole is not rotating. It is just, as Nathan says, the singularity. And in general relativity, of course, we understand gravity as a warping or a curving of space-time. So if I could show you a little comparison picture here, a normal star like our sun, if you compute the curvature of space-time around it, you find that it mostly obeys Newtonian gravity with very, very slight deviations. So you can think of the gravity of our own star as being a mild warping of the coordinates of space and time. You'll remember in RGR calculation, we tried to do gravitational time dilation for the Earth, and we found that there was virtually no gravitational time dilation for a mass such as Earth. And you'd find the same thing for an object the size and mass of our sun. Now, a neutron star is a general relativistic object. Its mass is so concentrated that the curvature of space-time in its vicinity becomes quite extreme. So the curvature of space-time, if you were to sort of plot the coordinates, would look a little more like this. In comparison to a star, in comparison to a black hole, the curvature of space-time around a black hole is sort of like the ultimate Super Mario Brother pit. And I'm talking about that old school Super Mario Brothers where you go, doo-doo-doo-doo-doo-doo, and you fall down and never stop falling. The curvature of space-time is infinite. And for a static, non-rotating black hole, it's kind of like it's like a puncture in the coordinates of space-time where the radius of curvature is infinite and there's sort of an infinite well surrounding the singularity. In this case, you can see, Nathan, that the coordinates of space-time are spherical. Remember, this is an analog for four-dimensional space. So this circle here is supposed to actually be a sphere, and you're curving the 3 dimensions of space into some other dimension like time. However, Nathan, it's clear to me from looking at this picture that in essence, the 3-dimensional component of the black hole is spherical. This is for a non-rotating black hole. Now, black holes do rotate. Most of them do. But it's complicated to calculate a rotating black hole. So we started off by calculating a non-rotating black hole, and we found that, yes, Nathan, it's spherical. The problem is, if you think about the conservation of angular momentum, when you collapse the radius of an object, any tiny amount of rotation that it begins with is going to speed up as you conserve angular momentum. This is why the sun and the planets are rotating today for the most part. Notice that neutron stars have extremely rapid rotations. The neutron star in the Crab Nebula has a 33 millisecond period, right? And that's collapsing something down to 10 kilometers. In theory, if you collapse an object down to 0, its rotation, in a sense, should almost become infinite. In other words, there's probably no such thing as a static Schwarzschild black hole. Presumably, all black holes have extremely rapid rotation. But here I'm going to get to the hook, Nathan. It turns out that in general relativity, if you compute the curvature of space-time coordinates around a rotating black hole, it turns out that the singularity itself, what used to be a microscopic dot, suddenly disappears. For this, I may need to go to my, where are we here? I need to go to my relativity lecture here, because I have a nice picture of the thing I'm trying to describe. And this is what the calculations in general relativity give you. This is the only other analytical solution you can make. The so-called Kerr black hole, the rotating black hole. And in such a case, Nathan, weirdly, the singularity disappears. And instead of all of the lines of space-time converging on a single microscopic dot, the curvature of space-time opens itself back up, the singularity vanishes, and you create something called a Schwarzschild throat, otherwise known as a
wormhole.
That's right. This is where the wormholes of science fiction come from. Interestingly enough, the wormholes of science fiction come straight out of the calculations of general relativity, and they're a completely realistic phenomenon. Unfortunately, okay, so where the science fiction enthusiasts get excited, and where we all get excited, is these are normal coordinates of space and time in our local universe.
Yeah.
The Schwarzschild radius is maybe here, right?
Okay.
And these coordinates extend to some other coordinates in space and time. But the big question mark, of course, is where are these space-time coordinates? Is this a different portion of our own universe or another universe? Are these like funnels?
Yeah, what I was thinking is like, you can kind of picture that, like, the, you know, where it kind of flattens out at the top and the bottom of the wormhole, like, though you can kind of picture that as a space.
That's normal space.
Exactly, but the throat of it, that would have to connect to planes or to a universe, dimension, whatever it would be.
Well, oh, sorry, you're not seeing my screen right now.
See,
Nathan,
you take a piece of paper and you bend it.
Well, I know that's the theory that that's our local.
Right. It could be more quotidian than another universe. It could be, you know, as they say in these sci-fi shows, a shortcut to some other another portion of the galaxy or another portion of space-time. It doesn't necessarily have to mean that this is a completely different universe. It could somehow connect. Our own universe has some global topology, some global curvature to it.
Yeah. That kind of brings me to a second question that I've kind of had for, like, since before I was in this class.
Okay.
Is there like a geometric, or is there at least a theory that there's a geometric shape to the universe?
Absolutely. Because gravity curves and warps the curvature of space and time, we believe that the entire mass content of all the galaxies in the universe should create a global curvature to the universe. And this is one of the fundamental questions that the branch of astronomy known as cosmology attempts to deal with. Now, before we, before we stumbled upon the dark energy thing, the sort of classical textbook definition of the possible curvatures of the universe. Do I have it in this slideshow here? I actually opened up a couple of extra slideshows in case you asked me about this. The three conceivable curvatures to our universe were, I definitely have a better picture than this, but in the interest of time, I'm just going to show you this one because it's available. Function F588. Now, keep in mind that these are three-dimensional analogs of what is a four-dimensional issue. Space-time is four-dimensional, so it's kind of difficult to represent it on paper. But what the calculations proposed to us originally was that the universe could have potentially three curvatures. One was a boring old flat universe in which space-time wasn't very curved, and that's basically like your big three-dimensional box universe. The other two that are kind of cute are a spherical geometry universe. This is where basically the entire universe would be a hypersphere, a four-dimensional sphere. And ever play those old video games like Asteroids, where if your ship goes off of one side of the screen, it kind of shows up on the other side of the screen?
Yeah.
That's sort of how a spherically curved universe would develop. It would sort of be finite in radius, and if you traveled forward in space in a straight line, in theory, just as you could circumnavigate a globe, you could come back to the same point again. There's a slightly more complicated one, which looks like a torus or like a donut. It's a saddle-shaped universe. This one has positive and negative curvature, and it's very, actually, you can prove that it's impossible to represent this saddle-shaped universe in a three-dimensional construction. Honestly, when I was a student, these were the three possible global curvatures of the universe, and that was all there was to it. Cosmology was just trying to figure out which one it was. Once they discovered dark energy, that the universe was expanding, that kind of threw a whole monkey wrench into these three curvatures, because a universe that includes a cosmological constant or dark energy can have a different curvature from all three of these, or it's kind of like a hyper accelerating universe. So it's a bit confusing. For years, the leading theory about the curvature of our universe was that it was on an expansion trajectory and that our universe would eventually fling itself apart and suffer a heat death. But what I understand from talking to my cosmologist friends is in recent years, the collapsing spherical shaped universe has come back in vogue. And that's kind of a happy or interesting philosophical thought. You know, of course, if we recollapse the universe back into a singularity, like the one that created a Big Bang, it's not a great leap in logic to imagine that the whole thing could start itself over again. And that's a comforting thought, because it means that we could be living out this universe in multiple cycles. And perhaps in a future universe, I'll finish my lectures on time. Maybe I'll show up on time. Maybe I'll even pay my taxes. Anything is possible in a future universe. But one thing's for sure, it's definitely not happening in this universe. Anyways, okay, you guys have busted another. I've actually 5 minutes over now, and that's uncool. We still have a little bit of problem set to do. So I know you guys have a million more questions, and I'd love to attempt to answer them, but we got a small job to do that'll take us about 40 minutes or so. Just 5 quick little questions on black holes and other fun things. Why don't I grab a cup of...
Quick thing about the shape of the universe.
Oh, yeah.
Professor Dave Kaiser from MIT does a great summary lecture on the state of cosmology at present, where he addresses the measurement of that one critical value that can determine what the shape of the universe is. Like
the critical density, I believe it is. The density of the universe.
Yeah, I mean, it has to be exactly 1 to be the flat case, right? If it's anything other than 1, then it's one or the other. It's the spherical or the saddle. And the measurements they've been able to do so far are converging very strongly towards 1. So it's kind of looking like things are flat. But anyway,
it's looking like things are flat, but I believe the presence, there's another twist to this story from what I remember. The presence of the cosmological constant means it's possible to have to have a universe that's at the critical density but still have a collapsing universe. I'm not an expert in the field, but I believe that.
I mean, I'm not trying to like. I'm not either, right? So all I'm saying is for the students who are interested in pursuing this further, to a good place to start might be to try and look up one of these David Kaiser lectures. I'm sure some of them have been recorded and are on the internet.
Hey, Zaz, do you have access to the chat? Do you have a YouTube link you can put in there? Because I'd like to see that too.
I'll see if I can find it.
It's probably not too hard to find, right? While we fish that up and I grab some iced tea, we'll do a real short break here, just like 2 to 3 minutes. I'll grab a cup of iced tea and then we'll solve some nutty problems together. Does that sound good, everyone?
Works for me.
Now, you all know what we're doing here today, right? We're doing chapter 18. We're doing those 5 problems.
I've already got the page pulled up.
Awesome. And you have the numbers pulled up too, Riker?
52, 53, 55, 56, and 61.
Hold on. And these are cute and fun problems on the subjects that we were just
All right, everyone heard that. Cute and fun.
Chapter 18. What
And
were
we
they
like
again?
freaking Care Bears.
52, 53, 55, 56, and 61.
All right, so I'm gonna grab some iced tea. I'll take a look too and see if I can. So David Kaiser, cosmology. I don't know if there was one Zaz that you thought was like much cooler than the others, much more interesting.
His Carl Sagan Day lecture this year, or last year, end of 2019, was a really good summary. And I'm just looking to see if it was recorded. It was called Quantum Jitters in the Sky.
Quantum jitters in the sky, cool.
Hey, Professor, I have a question for you.
Yeah.
If you have a second.
I have a second. I got many seconds.
Good lucks. So when you say that, so exam week, what's kind of like the rundown for like the class? Is it going to be another
You're
lecture?
gonna love this. Exam week, nothing. No exam, no nothing.
Oh, sick.
I mean, unless Marcus, is there something that you want to happen? I'm at your disposal.
Actually, my second question was going to be, so I resubmitted a bunch of the homeworks and labs. It says submitted, but there's still like nothing put in place.
Right. Yeah, I'm going to explain what's happening there. What's happening is I haven't graded anything in like 2 weeks. Okay, so
all right, good news. I love it.
Marcus, I have your submissions. Okay.
Lovely.
I can see them there. And I told myself today, since this is my last lecture of the semester, the only thing standing between me and pina colada time is your ungraded papers. So what I need to do is I'm going to sit down and I'm going to brute force my way through them on the quest towards pina colada time. Okay, so
Just give them
today's
A's.
the final day. I must grade your papers so I can put this class to bed. But Marcus, so I can understand your concern. You're concerned that you've been submitting things, but you haven't seen any grades popped in. So
Yeah.
I think I'm now 2 weeks behind. But it doesn't take me very long to grade them because I'm going to grade them leniently, and I just need to I need to dedicate some time. You know, there's kind of a reason why too. Everybody was submitting stuff late, and they were submitting them in like chunks and packets. So it was getting kind of frustrating to grade them because I would like grade 20 papers, and then like 2 more papers would come in, and then I'd say, well, I could wait to grade these papers, or eventually I just decided I'm just going to wait till everything's in, and I'm going to do it all at once, machine gun style, you know?
Yeah, I appreciate that though. You're a real one.
Okay, cool, but we can
also because you know how they're doing pass fail grades for most of the classes
right
this semester. So I strategically put you in another class as the only 2 classes that I'm getting a grade for.
Yeah, I think that's a good idea.
You made me the thumbnail.
You made his chicken the thumbnail.
What's this?
You made. I'm the thumbnail
did
for
you
the
see
last
that?
video.
No, that worked out so great. For any of you who weren't here last class, Nathan brought his chicken to the class, and
that'll get
the
the views
chicken
in.
is like.
That's
Honestly, I
Clickbait
wanted
title.
to make you the thumbnail, but I couldn't figure out how to do it, and then YouTube just magically did it for me. I was like, "Oh, this is so
That's
great."
so funny.
With the damn
Said
thumbnail.
that's the most interesting part.
Say that,
I was-
Morgan.
YouTube decided that the chicken was the most interesting part.
I was gonna say the same thing, Morgan. Absolutely. But anyways, sorry, Marcus had asked that question. If you look in my needs grading section, I have 173 items to grade.
Oh my.
And Marcus,
And look, it's all Marcus at the top. He's been waiting for so long.
see, Marcus, the good thing is that means that you're in there, okay? So your homework is securely recorded. And I honestly, it doesn't take me that long to do this. So in a couple hours, I'll have this banged out.
You're good. Take your time.
Hey guys, Zaz shared us the link for the quantum jitters in the sky. If you want to see a totally badass lecture in cosmology from MIT.
Anyone else sad Raph isn't here?
Yeah,
I'm
he's
very
like,
sad.
Wait, he's not.
Zaz actually took
Didn't
me.
show up
He
to the
took
last
me
one.
to on a guest lecture at MIT to see Max Tegmark. He's a world famous cosmologist, and he gave a super cool lecture at MIT on the subject of digital physics, which is kind of this, you know, plausible but out there hypothesis that if the universe is quantum and if it's binary in nature, that it's inherently something akin to a simulation. And these guys are top researchers in their field, and the lecture had a bit of cosmology in it, and it was really awesome. So my point that I'm trying to make is this link that he sent us is probably going to be some really cool stuff, and we should all watch that while we have our Cheerios after class today. All right. If you guys are ready to go, I'm ready to go. You want to crank this thing out? You want to beast some problems?
Yeah, let's do it up.
All right. Riker, if you've got the words, we need to hear them. Let's start with chapter 18, number 52.
So 52, a black hole 1 question mark is your title. You've just discovered a new X-ray binary, which we will call Hype X1. The system Hype X1 contains a bright B2 main sequence star orbiting an unseen companion. The separation of the stars is estimated to be 20 million kilometers, and the orbital period of the visible star is 4 days.
Okay, hold on. So this is an important problem because, as you know, most of the time we are not capable of directly imaging neutron stars, white dwarfs, or black holes. So oftentimes we see a case where we see a single star that's wobbling around an unseen point whose light cannot be detected. And we have to infer whether it is a white dwarf, neutron star, or black hole based on its mass. Now, you guys will remember the mass ranges for these. A white dwarf is only a star that's less than or equal to 1.4 solar mass units. Neutron stars are anywhere from, let's say, 1.5 solar masses up to 3 solar masses. That's a neutron star. And a black hole will be anything that's over 3 solar mass units, because that's the escape velocity of light. Now, you've given us the separation is 20 million kilometers. Was that right? 20 million kilometers?
20 million kilometers.
And did they give us an orbital period?
Orbital period of the visible star is 4 days.
Okay. This sounds like a job for what formula, students?
Well, I didn't actually read the question yet.
Oh, okay. Sorry.
So part A, use Newton's version of Kepler's third law to calculate the sum of the masses of the two stars in the system.
All right. So they already
give the answer in both kilograms and solar masses.
All right. Screw kilograms. That's a total waste of our time when we're dealing with stars. We're just going to get the answer in solar mass units.
You got it.
You guys remember the kiddie version of Newton's version of Kepler's third law? The kiddie edition? That'll make mincemeat of this problem here. Man, it's a good thing we're not doing a final exam, huh? Jenna, this homework is
18.
Bloody hell.
It's number 11.
Thank you, Morgan. Homework number 11.
Oh, right.
What's the kitty edition? What the hell is Newton's version of Kepler's third law? What's your name? What's your favorite color?
4 pi squared.
No.
Fake.
That's the hard one, Tim. That's the MKS units version. We want the shortcut. We want the Keplerian units version.
Ah, crap. Let me go to my notes. I know I have it
Anakin, do you know what it is?
Kind of, but I forget which ones, like in which direction you divide it, which one's on top, which one's on bottom.
Uh-huh. Well, okay, one of you has to find it. That's your job.
In the meantime, I can
here
go
it
get
is.
my rooster.
Mass total.
Mass total equals A3 over P squared. Where
So the
A3
total mass, of course, is the mass of the B2 star plus the mass of the mystery question mark object, the degenerate companion. And that's just simply going to be A cubed over P squared. What units do I require?
A cubed would be in AU, and P squared would be in years, and the mass would be in solar masses.
Okay. That means this is one last chance for me to school you in dimensional analysis, right? Let's start with our 20 million kilometers. How do I convert that to astronomical units?
Isn't it 150 times 10 to the 6th?
Where does that go, Nathan?
On the bottom.
Okay. So what's 2 over 15?
2 over 15.
I mean, it's what it is, right? Everything else cancels. I get 13% of an AU. How about these 4 days? I'm sorry, am I going too fast for you guys?
Not that much faster. It just takes me a second to write the notes down.
Yeah.
All right.
That's kind of what I'm doing. It's taking me a minute to write.
Okay, sure.
Yeah.
Isn't it 4 times 1 over 365?
Yeah. So 1 year is 365 days.
Ouch.
That's like 0.01.
Yep. 100th of a year. Okay. Now look, I gotta erase some stuff if we're gonna plug it into the kitty edition, right?
Hold on, let me just.
I'll do it up here. I like keeping my diagram up. So the total mass of my system then is 13% of an astronomical unit cubed over 100th of a year squared. Punch them up. Before COVID-19 decimated our downtown, there used to be a guy who'd sit on the steps of the city hall there. He was a shoe shine guy. And when you walk by, he'd go, "Shine 'em up." So that's what I'm telling you guys to do here. Shine 'em up.
$21.9.
Sorry, Morgan?
Isn't it like 22?
22? And the units?
Solar mass.
Solar mass?
That's solar masses.
Box it up. That's our total mass. And that's the answer to part A.
Okay.
All right, Riker, what's part B? Hey, hold on. Students, can I erase the bottom junk?
Second.
Sorry, did someone say 1 second?
Yeah, me.
Thinking about tomato juice. Let me just peek across the aisles here and see who's working. Nathan's good. Okay, I'm gonna erase the bottom stuff. Right? Riker, what's up? Part B.
All right, part B. Determine the mass of the unseen companion. Is it a neutron star or a black hole? Explain. Hint, B2 main sequence star has a mass of about 10 solar masses.
All right, that seems pretty easy enough, right? What do I do?
That's simple subtraction.
Yeah, that's my point.
It's 12 solar masses.
What's my unseen companion?
Black hole.
Yeah.
How come they couldn't just do this with Cygnus X1?
Cygnus X1, they did do this with Cygnus X1. Cygnus X1 was the first indirect detection of a black hole. And
isn't there a problem though with trying to calculate the distance?
Okay. No, not necessarily. There's two ways you can do this. Tim, remember that in chapter 15, we learned that there's a binary star orbit formula. And if you assume that the orbit is close to circular, you can calculate the semi-major axis based on the velocity and the period. So what likely happened with Cygnus X1 is they probably used the Doppler shift to measure the velocity of the main sequence component. And then they plugged it into the period formula, and that allowed them to compute the radius of orbit. Now, I don't know the details of what they did on Cygnus X1, but there's two different methods.
There's something about the angular size was too small for us to measure.
Then in that case, you've got to do this. If the angular size is too small, you use spectroscopy. This is why spectroscopy is so much more powerful than imaging, Tim. In imaging, you're dependent on whether or not you can see what's going on in that microscopic dot, and usually the answer is you can't. But with spectroscopy, as long as you can get light from the main sequence star, you can measure Doppler shifted absorption lines. If you have a velocity and if you have a period, you can get a reasonable estimate for the orbital separation. Okay. Now, yes, that does require you to assume the orbit is circular. But if the orbit is 80% eccentric, it'll only introduce a 20 or 30% uncertainty in your calculation, which is acceptable. You'll still get a rough idea. But cool question. Okay, that problem is done. Let's move on. This is a very fast homework, students.
So I'm gonna, summarize the next one real quick.
Oh, can I erase first? Is everyone okay with erasing?
Yep, I'm good.
Basically, the next one's the same problem again, right?
Same problem, but slightly different.
Okay. This is called a hypothetical black hole too?
Yeah, a black hole 2 question mark. Yep. So this is Hype X2. This one's a G2 with an unseen companion. Period of 5 days and a distance of 12 million kilometers. But same questions otherwise.
Basically, I assigned these two to be the same for a reason. Just like Tim knew about Cygnus X1, this is walking you through like the basic background of how they determined it was a black hole there. So let's do the same calculation again. We have 5 days. We're going to convert that to years.
That should be about the same, shouldn't it?
Wait, were the periods the same?
No, the period was 1 day more, but
Okay. Well, this time it's 0. We'll use 2 sig figs. We'll keep a second sig fig. The other one was 0.010. And here we have 12 million kilometers. I don't know what 12/15 is, but
wrong device.
sorry, 12/150ths. Does that look good to everyone?
0.08, yep.
All right. Now plug this in. Total mass of the system is 0.08 AU cubed divided by 0.014 days squared. Shine them up.
You really missed that shoe shiner, don't you?
What, isn't it years, not days?
Except that what I start saying is punch them up.
Isn't it year, not days?
Say that, Morgan?
Years, not days.
Sorry. Yeah, Morgan, you're right. I was just testing you to see if you were paying attention.
Yeah, sure.
Clearly Morgan's paying attention, so she'll get high marks.
I was just waiting for you to notice.
Waiting for you to notice.
I wonder who's calculating here.
Yeah,
Hey, Ellis, what's the answer?
Michael is.
Ivy, Jenna, Sal. Sal, you look.
2.6.
Sorry?
2.6.
I also got 2.6.
2.6
solar masses.
Thank you. Okay, so now in part B.
Neutron star.
Yes, that's right. So the mass of the question mark then is, oh, wait, hold on a second.
Oh, wait.
Oh, your
Yeah.
robe. That's the total mass, Nathan, right?
Didn't subtract it. My bad.
What's the mass of a G2 star? You should know this without looking it up. What is the mass of a spectral type G star?
Anywhere between, on
Huh?
about 1 solar
0.1
mass.
to 2.
Just one. It's the same spectral type as our sun. The mass of the unseen companion then
Is
what?
1.6. It's a neutron. Is 1.6. It's a.
Oh yeah,
neutron
sorry,
star.
Nathan is correct. It's a neutron star. Can't outfox you, son.
Wow. Born and bred genius.
All right, that's 2 down. Yeah, and I'm glad Tim chimed in with that. These aren't just random problems, but these are a reference to the famous first indirect detection of a black hole, Cygnus X1. It's an X-ray binary. By the way, the X-rays come from the accretion disk surrounding the neutron star, whereas the visible light comes from the main sequence component. But we detected it as an X-ray source first. I had so much to say about that, but so many things I wanted to tell you guys.
Never enough time.
Nope.
You could tell us for free.
I could tell you for free.
Yeah.
Or for a nickel.
All right.
We could haggle over this. There's a famous picture of the Milky Way. All right, so fine, I'll tell you for free. Not going to be long about it, but the famous picture of the Milky Way, if you look at the Milky Way in X-ray with the Chandra X-ray Observatory, unlike the normal image of the Milky Way at optical, where you can see all of these, you can see the disk and the bulge and whatnot. This is what the Milky Way galaxy looks like if you measure it at X-ray wavelengths. Now, I need to walk you through this here. First of all, you can't see the disk of the Milky Way at all. First of all, compare this, just for anyone who's here today. The Milky Way in the optical looks like this. And when you look at the Milky Way in the optical, why don't you guys impress me with what you've learned? What are we looking at here? What am I seeing when I look at the Milky Way at optical wavelengths?
You're basically seeing the bulge and all the dust.
You're seeing, yeah, you don't see much because you see the dust lanes, but you can see the outline of the disk and you can see the bulge. So the moral of the story is you can kind of see the sombrero shape of our galaxy, but much of the light is occluded by these dust lanes. Compare that picture with this picture of the Milky Way taken at X-ray wavelengths. It's totally fucking different. Gone is the bulge, gone is the disk. Do you want to know what all these are? All of these are just X-ray point sources. They're mysterious sources of X-ray light. And do you want to know what every single one of these things is?
A universe.
No.
I mean galaxy, sorry.
No, this is in our own Milky Way galaxy.
Oh.
It's not a galaxy at all.
A black hole?
Well, it's either a black hole. This is what's going on. Your function F5. Wait, let me go to the picture of Cygnus X1 here. They could be black holes, but they could also be neutron stars or white dwarfs. Shoot, I already forgot the stupid number of that slide. Sorry, I have to keep I'm not good at multitasking, guys. Just 99, that's what I want. Function F5, 99. What happens is when you look at the Milky Way at X-rays, you're basically not seeing any visible light. So you don't see the stars at all at X-ray wavelengths. You obviously aren't going to see black holes at X-rays because black holes don't give off any light. But remember that a lot of these stars are in binary companions in which the binary companion, whether it's a neutron star or a black hole, they start slurping plasma off, and the plasma gets spiraled around into a super hot ring of gas called an accretion disk. It's the accretion disks that are giving off the X-rays. Basically, those little disks surrounding the compact objects are so hot that they undergo bursts of nuclear fusion, and they actually give off X-rays into space. So what's cool is when you look at the Milky Way, it's directly related to the questions we were just doing. When you look at the Milky Way at X-ray wavelengths, what you're seeing in that image there, shoot, go away, go away, go away, go away. All of those point sources you're seeing, these are all X-ray point sources, from accretion disks. Now, in a sense, you're looking at all of the dead stars in the universe. Some of these are neutron stars, some of them are white dwarfs, and some of them are black holes. The only way to tell the difference is by doing the calculation that we just did. What happens is usually you'll pick a target, like you'll say, okay, here's an X-ray point source. I'm interested in figuring out what this is. You then take an optical telescope and you point it at the same coordinates, and you'll find a little single main sequence star there, and you'll notice the main sequence star is wobbling. You calculate the period of its wobble, and you infer the mass of the unseen companion, and then you use the technique that we just used right here. Depending on the mass, you conclude, aha, this is a neutron star, this is a black hole. So that's the thing that I wanted to tell you for free, Morgan. I'm not even going to charge you a nickel, is that you can actually see all these X-ray sources just by looking at the Milky Way galaxy with an X-ray telescope. That's why X-ray telescopes are so cool. Okay, I'm erasing. Is everyone okay with that?
Yep.
All right, 55. What happens?
All right. Neutron star density.
Yay.
A typical neutron star has a mass of about 1.5 solar masses and a radius of 10 kilometers. So part A, it wants us to calculate the average density of a neutron star in kilograms per cubic centimeter.
Okay. let's convert to kilograms and cubic centimeters right away. What's the mass of the sun?
It's in the other notebook.
I'll just tell you, it's 2 times 10 to the 30 kilograms. What's 2 times 1.5?
3.
So that's 3 times 10 to the 30 kilograms. We have to calculate this in kilograms per cubic centimeter. So now we have to convert 10 kilometers. Give me some numbers.
Convert it to meters and then convert it to centimeters.
I like what you say.
So,
all right, so
1 kilometer on the bottom.
Yep.
Equals 1,000 meters.
Yep.
And then 1 meter on the bottom is 100 centimeters.
And what's that give us if we plug all those zeros together? Do it in your head. You don't need a calculator.
1 million?
Yeah. Nice, Riker. Okay. Let's go ahead, and the density of a star is 3 times its mass over 4 pi r cubed. That was directly from lecture today, right?
Yeah.
All right. So plug in our numbies. 3 times 10 to the 30. 4 times pi times a million centimeters cubed. Punch them up.
$7.2.
I got 7 times 10 to the 11.
7.2 says Morgan.
Yep, that works better.
Well, either one is good. And what are the units again?
It should be kilograms per cubic centimeter.
So that's 720 billion kilograms per cubic centimeter. That's part A, right?
Yeah, give me a second. I'm not done writing this.
That's okay. Just take your time, guys. Get it up.
Hey, while we're waiting for that, does anyone have part B to the last one? I missed it.
Yeah,
Oh.
I've got it.
I asked if you were ready to go.
I know. I'm dumb.
At least he acknowledges it.
All right.
Yeah, see?
Yeah. I need some coffee.
Sorry, Tim, I could not see that.
I'll be done soon enough.
Thank you, Tim.
7.2 times.
I'm ready to go when you guys are. Just let me know.
I'm ready.
I will be in a second.
All right.
All right, I'm good.
You sure? Take your time. It's the 12 Musketeers here, whatever we got.
23.
Brilliant green. Okay. We ready to party?
Yeah.
You know it.
I'm going to erase. Riker, what's part B?
Part B. Compare the mass of 1 cubic centimeter of neutron star material to the mass of Mount Everest, which is approximately 5 times 10 to the 10 kilograms. God damn.
Right? That's what I'm saying. So here we have 1 cubic centimeter, which is about, it's about the dimensions of a chicken bouillon cube or a dice, right? And the mass of 1 centimeter cubed is what Mike said before, 7 times 10 to the 11 kilograms.
If my math is correct, isn't that 1 kilogram? Isn't that 1 cubic centimeter of neutron star? 20 times denser than Mount Everest. If my math is correct.
Well, not denser. It's billions of times denser. It's 1 cubic centimeter is more.
There's more matter.
Yeah. What's 70 divided by 5?
Oh, 12.
14.
No, not 12. 14.
"14 times more massive than Mount Everest." In other words, to compare to the density of a neutron star, you'd have to take Mount Everest and smush it into this volume of a dice.
What about Olympus Mons?
Olympus Mons is certainly taller, Nathan. But remember, the surface gravity, one of the funny things I didn't get to tell my Astronomy 1010 students about this semester, Mars is smaller than Earth. And because of that, its gravity is weaker and it doesn't compress mountains the same. So I don't think the density, well, it's difficult for me to know how Olympus Mons would compare. One of the reasons Mars's volcanoes are taller is because they don't compress rock as intensely on Mars. The G-forces are not as intense. Hey, you know what I just realized that I screwed up? Because I didn't take a proper break, I did not stop the lecture and start the office hours.
Oh no. Oh well.
Well, they'll figure it out.
It's just going to be one big, long video.
They probably.
I mean, that's how it is for us.
Put timestamps.
That's true. Yeah, I should. Do I know how to put timestamps? I'll have to figure that out. Fudge. Okay, yeah, I just realized that I didn't make the psychic break between lecture and homework. Whatever. That just means they have to suffer through a little more of me to get to the answers they need.
Yeah, now they have to know what it's like to be
Season finale. Yes,
The season finale.
Yes.
upload it to YouTube.
Hello at the season finale. I'm totally going to put that in the. Okay.
Description for timestamps.
Yeah, I should put some timestamps. I don't know how to do that, but it shouldn't be too hard. Okay, can I erase?
Yep.
No.
Oh, no, okay.
What does it say after 14 times?
More massive than Mount Everest.
Thank you.
Is that all of it?
Yeah.
All right.
Or that's all of 55.
But
Wow.
Yeah, I was gonna say.
Isn't tight.
Say,
Thank you. Thank you. Woo.
What have you done?
Thank you again.
was fine. So
Sorry, me and Marcus were hanging out. And I'm not feeling great.
Uh-oh. You coming down with the Rona?
That was the joke I was making, yes, but I'm fine.
Marcus survived it.
I am. Yeah, it's true. If Marcus can survive it, then I'll probably be fine.
I think we lost
Could have had it already. That's what he gets for leaving. If you leave, you get sass.
Sorry, is anyone still writing?
No.
All right.
I'm not.
It's hard for me to know, guys, when you're done, so. All right. Number 56.
So this one's a three-part. This one's a four-parter.
Oh, lovely.
Christ.
boy.
Oh, quit your whining.
Title?
Schwarzschild radii. Calculate the Schwarzschild radius in kilometers for each of the following. We're literally doing the same equation 4 times, people.
And it's, remember, hold on, can I say something? There's 2 versions of this formula, and 2 of them are, come on. Come on, focus. Look, my knuckles are in focus. Isn't that weird? It just suddenly goes to like.
Your knuckles look great, though.
it's a ghost.
I got some fine knuckles.
It's
Not focus again.
It went to
Oh,
shit
no,
again.
we can't even tell the writing on the board. There it is.
2gm over c squared, or there's the shortcut, the kiddie edition.
3 km times the mass in solar units.
Right. And that's why, even though this is 4 parts, guys, this is a wicked fast question. Okay, what's part A?
10 to the 8th solar masses.
What's the object?
Black hole in the center of a quasar.
So that's a supermassive black hole. Okay. So which version do we want to use?
3 km times m.
Couldn't be any simpler, guys. 3 kilometers times 10 to the 8 solar masses.
300 million.
Yeah. Which is 8 divided by 150 e to the 6. That's about 2 AU. So even a supermassive black hole is only twice the size of Earth's orbit. Okay, what's part B?
Part B is a 5 solar mass black hole that formed in the supernova of a massive star.
That's pretty easy, right? "15 kilometers. Part C.
Ah, crap. Part C, a mini black hole with the mass of the moon.
The mass of the moon is 7 times 10 to the 22 kilograms. We should probably use the MKS version for this. The Schwarzschild radius is 2 times 7 times 10 to the minus 11. I'll do this in purple. Meters cubed per kilogram per second squared. times 7 times 10 to the 22 kilograms, all over the speed of light squared. Punch him up.
Oh, now we
3
got to do the
times
long one.
10 to the 8th or 9th?
8.
Oh, now we got to do the long one.
I see. You can't read it. That's what you're saying.
So the mass of the moon is what?
7 times 10 to the 22 kilograms.
All right, so hold on. This is a pain in my ass.
M-O-O-N. That spells moon.
Where's that from?
What is that from?
Fuck. What is that from?
Baby. That's the stand.
The Stand, right? The Stand.
Yes!
Stephen King. The made-for-TV Stephen King.
1.1 times 10 to the negative 4.
I remember. Yeah.
Greg knew it. Greg knew it.
You do it too.
1.1 times 10 to the negative 4.
I've only seen that movie once.
What are the units?
Read the book.
Like kilometers.
Remember when they played the Blue Oyster Cult and they show all the dead bodies dying of the virus? Kind of a good movie to rewatch these days. What are the units?
Meter.
Meters.
How many millimeters is that? My metric-loving friends.
1.1 times 10 to the negative 1.
All right, or put it in plainer English. That's 1 times 1 to the negative dumb. Don't. Oh, we should watch Blazing Saddles. Yeah, we need some.
Yo!
Wait, what's
I'm in.
1.1 times 10 to the minus 1, Nathan, in plain English? Like no scientific notation.
Oh, 0.11?
Yeah, millimeters. It's a tenth of a millimeter. What's a tenth of a millimeter? Like the head of a pin? Maybe?
Something like that.
I don't know.
You'd have to compress the moon to the head of a pin to make it a black hole.
Too small to see.
I know the Earth is a peanut.
I think it's about the size of a marble.
Yeah, well,
Earth
peanuts
is
and
like a
marbles.
centimeter or 2.
Next question. What would you have to compress the Earth down to?
I can
I don't
tell
know.
you faster than you can tell me. 2 times 7 times 10 to the minus 11 times 6 exp 24 divided by
I'm just gonna
3.
get 2 centimeters.
Damn it.
9 times 10 to the minus 3 meters. 9 millimeters
Sorry,
for the Earth. It's about a centimeter. It's about the size of a marble. Okay. What's part D, Riker?
Please be Earth.
No, it's not the Earth for part D.
Aw.
Please hold. A mini black hole formed when a super advanced civilization decides to punish you, unfairly, by squeezing you until you become so small that you disappeared inside your own event horizon.
All right. What's the mass
That's
of you? What's the mass of a human?
I don't know.
It's like half your weight, right?
All right, yeah, we did this. It's like 80.
80 kilograms, right?
Yeah, compress me. I'm ready.
You will impress me and I will compress thee. Here we go. 2 times 7 times 10 to the minus 11 meters cubed per kilogram per second squared times 80 kilograms all over 3 times 10 to the 8 meters per second squared. Hit it.
Please hold.
1.2 times 10 to the negative 25.
Meters.
Right.
Yeah.
Why don't we convert that to some more reasonable unit? What do you think a more reasonable unit is for 10 to the minus 25 meters? Shall we share screen and look for small numbers together? We could convert it to attometers. We could convert it to femtometers. Let's see, we're looking for 10 to the minus 25, right? Or something
How
close.
low
Ooh,
can we go? Septillionth?
no.
Oh, yocto.
Yoctometers. A yocto is a negative 24. So how many yoctometers is that if it's 10 to the minus 24?
That's 10 yoctometers.
No.
No?
No, because you're going to the other side of the decimal point, right?
Oh.
1
0.12 yoctometers?
Not one.
No.
0.12.
0.12.
That'll do wonders for my waistline. Thank you. Thank you. I'll be here all week.
I hope not.
So you're a tenth of a yoctometer is how you need to squeeze yourself. Okay, not bad. One more to go. Final problem of astronomy 2020.
Wait, what is under the meter 3? I can't read that. Is that GSK? Yes.
Meters cubed per kilogram per second squared. I'm sorry. I'll write it up here, Bella. It's
Thank you.
Cubed per kilogram per second squared. I was trying to go quick. The units of G are unruly. Damn, we'd be busting out the yoctometers for our final problem set here. This thing's off the chain.
All right. I don't know how many parts this has, so let's get it.
Nathan, I'm glad that you're still removing your diddly bobs, even long after we meet in person. He knows the importance of good diddly bob hygiene.
I'm all set.
I haven't even been pulling them out of my notebook.
I'm all set.
Okay, can I erase students?
Yeah.
Wait, I think I'm taking a photo. Wait.
Gonna ask me for help with
No,
those
no,
daily
she's good.
bobs.
Jonathan, did you need a minute?
Nah, I'm good.
Mike, did you get your photo?
No, yeah, I'm good.
Did you get your precious photos?
Shut up, Paul.
The last question.
Yeah, 61. Right.
2 semesters worth
Hey, Nathan.
of this.
So, challenge problem. A neutron star comes to town.
Oh no.
Challenge.
That does sound like a problem.
Gotta get him out of here.
I thought Barrington was a gated community.
Okay, Riker.
Okay. Suppose a neutron star suddenly appeared in your hometown. How thick a layer would Earth form as it wrapped around the neutron star's surface? Assume that the layer formed by Earth has the same average density as the neutron star. And consider the mass of Earth to be distributed in a spherical shell over the surface of the neutron star, and then calculate the thickness of such a shell with the same mass as Earth. The volume of a spherical shell is approximately its surface area times its thickness. The shell equals 4 pi r squared times thickness. Because the shell will be thin, you can assume that its radius is the radius of the neutron star. Jesus Christ.
He's our Lord and Savior.
Neutron star rolls up on a horse.
Jesus Christ himself couldn't save you from neutron star compression. Let me tell you, this problem is not as bad as it looks at first, okay? They call it a challenge problem, but it's not much of a challenge.
You.
Ooh.
Yeah, I was about to say, says the guy with a fucking degree.
Yeah, I don't even have my associates.
You can handle this. You guys can handle this.
They're trying really hard to stop me.
Let's see, since this is our last problem, let's see if we can do this together with the hive mind, okay? I'm going to represent the thickness of my shell with a little delta tau. Delta tau is the thickness. So that's this thickness here. And that's what we're trying to compute. Obviously, you guys understand what's going on. Earth is bigger than a neutron star. Because a typical neutron star, let's do the same one that we did in that previous problem. And what was that problem? I think it was 55. From problem 55, we had a radius of 10 kilometers. And what was our mass?
1.6 solar masses.
1.5 solar masses.
1.5 solar masses.
And we're actually going to need the density from that problem. So what did we get for the density?
7.2 times 10 to the 11 kilograms per centimeter cubed.
That's going to help us here. Now, we know the density, we know the mass, we know the radius. Remember that Earth is much bigger in radius than 10 kilometers, but Earth is much smaller in mass than the neutron star. So what would probably happen is when the neutron star comes to town, the neutron star would actually first burrow a hole through the Earth, and it would fly towards the core where the Earth is densest, and the neutron star would actually pass through the core because of its momentum, and then it would turn around and oscillate through, and it would basically start slicing the Earth up into Swiss cheese, plunging holes through the Earth. And each time it passed the core of Earth, it would slurp more and more material onto it until eventually Earth actually got compressed and wrapped around the surface of the neutron star. Eventually, this would be the mass of Earth, but compressed to some new thickness. The secret sauce to this problem is recognizing that whatever this layer is, it can only contain the mass of Earth, but we know that it needs to be compressed to this neutron star density. Where should I go from there, class? If my goal is to find the thickness, we have to mentally leapfrog over stones until we get to thickness. So rather than trying to get the thickness right away, what's some intermediary? It helps to work backwards. For instance, the thickness is related to the volume of the shell. I'm stumped. I don't know what to do.
Didn't they say that
I feel like you do.
it was like, didn't it say that it was so thin that it didn't matter? Like you basically were just using the radius of the neutron star?
What they meant by that is, okay, so normally for a volume, the volume of a sphere is 4/3 pi r cubed, right, Nathan?
Mm-hmm.
But here, what we're doing is we're saying, since the radius is thin, okay, here's my analogy. Do you know how if you had to calculate the volume of like a pizza box, you could just take the area of the pizza box and multiply it by its thickness, right? They're saying that even though the radius is growing a bit, since the radius won't be growing by that much, you can almost treat this like a pizza box, where you take the surface area of the star and you multiply it through a little delta t, and that's going to give you the volume of the shell. Did that make sense? Maybe that didn't make enough sense.
It made more sense than...
Okay, for instance, if you were going to double the radius of your neutron star, the volume of that shell would not simply be surface area times delta t, because you'd be growing the radius by a significant fraction. But if the radius is just going to raise up by a few centimeters or millimeters or whatever, basically the radius is still close enough to 10 kilometers where you can just crudely multiply the surface area by the thickness. And it's kind of like taking the surface area of a box and multiplying it through its thickness. You see what I mean?
Mm-hmm.
All right, you'd have to think about that for a minute. In other words, they've already given you the equation, Nathan, for the volume of a shell, surface area times thickness. Your goal is to solve for this. I'm going to give you guys a hint. We can already solve for the surface area of the neutron star by using the formula surface area is 4 times pi times approximately the radius of the neutron star squared. Let's get that in cubic centimeters. From problem 55, what does 10 kilometers come out to be in centimeters? I think it was like 1,000,000 centimeters, right?
Cubic centimeters.
No, just regular centimeters. It's a linear dimension. Anyways, punch that up.
Wait, 1.3 times 10 to the 13.
1.3 times 10 to the 13, Morgan?
Yeah.
What are my units?
Centimeters, right?
Squared. Can somebody else verify that, please?
It's good. Yeah.
All right, cool. All right, here's the moment of truth. What do I do next? I want you guys to figure out the next step.
Calculate the volume.
Yes, Tim, you're correct. Tim's saying, I think Tim's logic goes like this. Well, I want the thickness. I know the surface area, so if I could calculate the volume, I'd be done. Okay, Tim, I like it when you say that, but how am I going to get that volume?
Is it 4/3?
No, you can't do that because this is a shell. This isn't a sphere, Tim. This is a shell. They've given you the volume for the shell as surface area times thickness. You've already used that up. You've got to get the volume through another stratagem. You need another strategy to get the volume. The hint is up on the board there. God, if I could just solve this one problem, I could drink a Bloody Mary.
You
I
do.
thought it was tomato juice.
It was before, but this is taking a toll on my psyche.
It's fermented.
It's fermented tomato juice. Yeah, fermented with vodka. All right. Hey, I'm sorry, you guys are so close.
I think he's pointing at the centimeters cubed for a reason.
I need to. Where am I stuck? What am I doing right now?
You're pointing at the density.
All right, but what am I trying to do?
Hold on. Density equals.
Yes, Riker. Breakthrough moment.
I don't exactly remember the equation.
You don't need that. Just look at the units and you'll know what the formula is. The units tell you what the formula is.
Divided by centimeters.
Divided by the mass. No.
That's not units of mass.
No. Density equals mass divided by the volume.
That's it. There's your breakthrough. What am I going to do?
So you're going to algebraically switch volume and density.
Yes. So volume equals mass over density. But what mass?
Mass equals 1.5 solar masses.
That's the mass of the neutron star. We're talking about
times the mass of Earth.
That's it. You've got to use the mass of Earth this time, 6 times 10 to the 24 kilograms over 7.2 times 10 to the 11 kilograms per cubic centimeter. Because here we're just talking about the volume of the shell, right? And that's only due to the mass of Earth.
8.3 times 10 to the 12 centimeters cubed.
Okay, I'm almost done. What should I do now?
Put it into the formula.
Which formula, Morgan?
The V shell formula.
Very good. So if I rearrange that, Morgan, my delta tau, my thickness, is going to be the volume of the shell
Divided by the surface area.
of the neutron star, or 8.3 times 10 to the 12 cubic centimeters over 1.3 times 10 to the 13 centimeters squared. Dragon's egg, where is it? I've got one last thing to share with you when this is done.
0.6 centimeters.
Fudge. Can I get someone to confirm that?
0.64.
We'll just go with 0.6. There's something here. Yes, it's behind here.
This is where he stored the dead bodies.
Okay, hold on. The final answer. That's what all of Earth would be reduced to.
That's sad.
A layer of neutron crust, half a centimeter thick on the surface of a neutron star. Now, I want to tell you how this relates to this legendary science fiction book by Robert Forward called Dragon's Egg. Okay, you guys may not know this, but there is a genre of science fiction called hard science fiction.
Heard of it.
The whole purpose is to be slaves to good science, and all artistry and plot and character development is secondary to just the hard science itself. And one of the exemplars of this field takes place on a hypothetical neutron star called Dragon's Egg. And why this book is so funny, even if you don't have time to read the book, you can just read the Wikipedia synopsis and get a good jolly out of it. But basically, the plot structure goes like this. These humans travel to a neutron star, and they discover living organisms, hyper-compressed organisms that live on the surface of a neutron star. They are called the Chila, and they are basically like little sesame seeds that are only about 1 millimeter in height, and the gravitational G-forces have smushed their bodies down and compressed them into these little like chia seeds. Now, what happens is, in the plot synopsis, the humans travel in the year 2020 AD to Dragon's Egg, and they find these Chila in a state where they're basically like at a Genghis Khan state of civilization, and the Chila are like living on the surface of a neutron star crust, and they're herding like, you know, neutron crystals around. Their eyes are 1/10 of a millimeter wide. And when the humans first travel to the Dragon's Egg, they decide that they want to contact these barbarian Chila who are in a primitive state of development. So the humans beam a message to the Chila, and they say, "Hello, Chila, we are Earthmen, we're here to visit you." Now, unfortunately, the gravitational time dilation causes the signal to take something like maybe a few seconds of human time, but it takes like several million years of Chila time, during which point their civilization advances to such a farther technological degree than the humans that by the time it's time for them to send the return message, they kind of are at a state where their technology is unethical to share with primitive human culture. So they kind of reply, oh yeah, it was nice to get to know you guys, but you're now too stupid for us to have an intelligent conversation with. So we think it's best if you go away. And that's the entire book. That's the entire story. It's basically 1 second of gravitational time dilation for humans. Since real-time conversations are impossible, the humans send sections of the expedition library. It's just, you got to read this whole thing. It's hilarious. The Chi-Lib decided that transforming the technologies far too advanced for humans would stunt humanity's development. So this book, Dragon's Egg, is kind of cool because it sort of imagines, would it be possible for life to exist on the surface of a neutron star? And what might it be like if we attempted to communicate with such organisms? So there's a plug for Robert Forward's Dragon Egg and hard science fiction as a genre. Check it out, or at the very least, read the Wikipedia page. I got a good chuckle out of it. I know you will. Does everyone have this material copied here?
Yep.
Yep.
Anyone lagging behind, or are you guys all caught up? Sounds
More like Dragon's
Egg.
Egg
Oh,
behind.
wait. Oh. Let me put
No,
this.
don't laugh.
Let me put this in the chat because that's cool to do. Boom. All right. So let's go back to, where am I here? I want to leave speaker mode. I want to exit full screen and I want to go. Okay. So that concludes Astronomy 1020. I wish we had more time to do stuff. Aw, thanks guys. I wish we had more time to do stuff together, but such is life. I'm sure many of you are ready for a little break before your summer classes start. I will be teaching Astronomy 1010 and 1020, both Summer 1 and Summer 2. So anyone who still needs credits, Tim, you got registered today?
I did. Are those classes going to be, like session 2 summer, is that going to actually be on campus or?
They don't know yet.
Yeah, the current plan is for us to do Summer 1 completely online. So I'm going to have an entire class like this online. And then the proposed plan at this point is for Summer 2 to be live. My suspicions are we're not going to be there yet. Well, I don't know. 7 weeks doesn't seem like a long time, but it also is a long time. We won't know for a little while what the plan is, but I'm hoping by fall we'll be back in person. If we actually get back together by Summer 2, that would be wonderful, but I suspect I'm going to have to run an entire course like this, which is going to be kind of tough because most of you guys got to have some time with me in person, which I think created a lot of goodwill that pushed this class forward. So I don't know what it's going to be like, meeting people for the first time online like this. I might have to rely on some of my veterans to set the pace and the tone for the class. And I mean my astronomy veterans. In any case, here's what's going to happen. You guys are going to submit today's homework and any labs you haven't done. And I have 172 papers to grade. They don't take very long to grade, so that's a good thing, but it's going to take me a while. But I think I can get this done by today or by tomorrow, if you guys can get everything submitted by tomorrow. So tomorrow is supposed to be like the cutoff for those of you who might not have had anything done. So some of us have some work to do, but we're basically here. We're at the end of our class. Make sure you specify today. Riker, did you say today was the last day to specify grade?
Today was the last day to specify whether you wanted a letter grade or just a pass-fail.
Before the end
Well,
of
today still is the last day, so if you want to, you can still do it.
You can still do it today, but if you don't do it by the end of the day today, you cannot.
Wow.
I
wish they had given us one more day for that, but okay.
Well, since a lot of classes have finished early, 3 of my classes finished 2 weeks ago.
Right.
Oh, that would have been great.
2 weeks ago?
Yeah, my business class ended 3 weeks ago.
Who's teaching that class?
I don't remember her
No
name.
rats. No rats.
Don't rat. No, I'm like, wow, that's like a total dereliction of duty there. But okay. Anyways, yeah, you're right. No rats. Okay, fine. Anyways, There may have been other reasons for that. You know, physics classes are tough because you really do need some heavy equipment for labs.
Oh yeah,
We were able to get through our labs in a sort of clever fashion, but I could see that being more challenging if you had to use air tracks and some other complicated machinery. So, in any case, no judgment here, guys. Oh, one other thing. I have given you the option to evaluate the course. If you care to evaluate the course, Paula walked me through this the other day, but you go to your CCRI, my CCRI, whatever that is called, pipeline or banner or whatever, banner I guess it is, and you log into your my CCRI, and there's a section for you guys to evaluate. For me, I had to activate this class. Mine was like somewhere down here. It's different for students. Whoa. I had to go to my For Faculty tab, but I think you have to go to a tab called My Classes. And I've enabled online evaluations for this course. So basically you select your semester, spring 2020, and you guys can fill out an online SRI, student evaluation. Darn, there were instructions for students somewhere.
You basically go to your class list of like your schedule, and then you click the link next to your class, and then it'll bring you to the thing that you have to fill out.
Yeah, you might have to click on my name, on the professor's name.
It's like,
that's if you want to do an evaluation, feel free. Okay. So are we in good shape now?
Yeah.
Yep.
I've submitted my homework.
My homework's submitted.
I have a question.
Yeah,
I
So,
need to submit it.
looking at the submissions things and stuff, lab 9, did we do that?
One of the labs we didn't do.
Okay.
I'm a little behind. Oh, this is 1010. I'm a little behind in my grading.
I know that because it says submitted on my behalf, in which I'm not waiting, like I'm not expecting the grade anytime soon. I just want to know.
I need to do that right away. I'm so embarrassed. I fell a little behind here, but we did do lab 9. We did binaries. We did lab 10 was main sequence fitting. Lab 11 was the twin paradox.
Can you tell me what page was that in the book?
Do you mean the textbook or the lab book?
The lab book. Oh, you don't know.
No, I can tell you. You're asking about the binary lab?
Yeah.
The way we can figure that out is quite simple. Let me share my screen with you. On Blackboard, we'll go to Lab tab. Binary stars was lab number 9.
Yeah.
Oh, I'm sorry. And what in the lab book, if we click on, I gave you copies, it's 14.
It is 14. Okay.
And you should have submitted the data sheet. You just had to submit this page, 14-9.
Okay.
Just
so I didn't submit it. All right. I just want to make sure on my behalf that I submitted.
Sure. Like I was trying to point out, Bella, the way you can check is just go through these labs and make sure that you have a submission for each of these. Lab 7, Lab 8, Lab 9, Lab 10, Lab 11, Lab 12.
Yeah. All right. Thank you.
You can always email me if you are still confused. You know, I'll try to help however I can.
No, because when you go on like on my Blackboard, if I go to the grading section, it'll tell me what I have submitted and what I haven't submitted.
Oh, okay, good.
So that's why I was like, wait a minute, I thought I did, but apparently I guess I did not. So
Oh,
I'm gonna
well, no, there's another thing too. Okay, this could have been my fault. I didn't know what I was doing the first time I set up Blackboard. And so something like, let me show you my full grading center here. I started out not realizing that the assignments would create a column for lab. and I like manually set up columns for all of these labs and homeworks. And then I like loaded the assignment. Basically, I didn't know what I was doing in Blackboard. So I think as long, you just have to make sure, honestly, I'm not sure how it works entirely, but as long as you have a submission for each of these doodads, that's what counts. Homework 6, homework 7, homework 8, homework 9, homework 10, homework 11.
Yeah, I'm gonna just resubmit some of these because it
Guys,
says upcoming on my
the second I end
side.
this lecture, I'm immediately gonna just start cranking out the grading. So hopefully by tonight or tomorrow, you'll be able to see what's there and what's not there. I thought that I could kind of wait and kind of grade people sort of at the end, not considering the fact that you guys would be monitoring this. I'm not used to you guys monitoring the grading as you go. So Bella, I can understand there's many of us and any one of us could forget to do a thing. So my point being, you check on your end, I'll do grading and check once more tomorrow, okay?
Okay.
Don't
Thank you.
All right, are we cool? I'm gonna stop the recording.